Hi. Well, if you're watching this DVD, that means that you went through the challenges of the first DVD covering units 1 through 7. Hopefully, you stopped it, you reviewed it, you got your system working out there, you're kind of feeling kind of good. We're now getting in the second DVD, and we're going to unit number 8, overcurrent protection of control conductors. This unit covers motor control circuits, how they're protected against hazards related to overheating in accordance with the National Electrical Code. You understand the fundamentals of theory, and that's why you're at this stage. Hopefully, you have some understanding of fundamentals of conductor sizing and overcurrent protection as it relates to the National Electrical Code. If not, if you finished our electrical theory course, that is covered in basic electrical theory, conductor sizing, overcurrent protection, and that just a little basic fundamentals having to do with that. So we're making an assumption. Do you understand what a breaker is, the time current curves, and differences between fuses, circuit breakers, one-time fuses, dual element fuses? If not, get that theory course, finish that course before you continue on, because now we're getting into some code. Let's keep going. Protection of control conductors. Overcurrent protection is based on the size of the conductor. Larger conductors, larger protection. Smaller conductors, the smaller the protection and capacity needs to be. We can use control conductors as small as 18 gauge wire, and those references have to do with the National Electrical Code, 43072. .72, 725.23. This has to do with class 1 control circuits, and this has to do with motor control circuits. We're not going to get to that right now. To properly select overcurrent protection for a control circuit, distinguish whether the control circuit is a separate control circuit or whether it is a common control circuit. So let's kind of identify those two terms. First one is a separate control circuit. A separate control circuit, you can see right here, we're coming off the auxiliary contacts, getting our 3-wire control. 1, 2, 3, coming over here. Here's a neutral coming down, going to one side. Here is our overcurrent protection. So this is a separate, well, since we're providing a separate protection for these conductors, we have to size that protection based upon the ampacity rating of these conductors. Note 1 of table 43072, column A, requires a conductor sizes 14 and larger be protected based upon table 31016. If you're an electrician or if you have electrical background, you should be familiar with table 310.16 and how you size protection for conductors. Let's go ahead and jump to the code, and let's go to 437. That slide said what? 43072B, column A. We are in Article 430. Relates to motors, motor circuits, and controllers. We are going into Part 6 of Article 430, which is motor control circuits. We are in Section 430.72, overcurrent protection of motor control circuits. And we are now looking at, I'll get the heading in here, Table 430.72b. And there's a column A, which talks about separate protection provided. And let's go to a graphic right here. Separate protection provided. Well, when you have this scenario, then the code says, well, if you use 18 gauge wire, provide 7 amp protection. Well, you're not going to get a 7 amp breaker, but you can get a 7 amp fuse. Well, then you provide 7 amp fuse protection. So not likely for separate protection for that size, but you might do that. A 16 amp circuit or 16 gauge wire would be a 10 amp. And then note number 1 says, well, look, if it's larger than, or if it's 14 and larger, note number 1 says go to 310.15 as applicable. And when you go to 310.15, it basically tells you to go to table 310.16. What are the common size conductors that you guys use if it's not going to be at 18 or a 6? Now, Dan, yesterday I think you said you use 18 and 16s quite a bit.
Yeah, we use 16 on most of our control circuits.
Now, do you have a separate overcurrent protection for the 16?
Yes, we do, because we have, most of our control is actually PLC, so we have separate by section of the
In
equipment.
the PLC, it has. Now, is there overcurrent protection in the PLC?
Well, all outputs do.
All the outputs have overcurrent
They
protection.
have fuses because they're triac outputs and they want to protect the
So you use an
electronic
18
part of
gauge
them.
wire, 16 gauge wire,
16 gauge, yes.
and your PLCs have, the outputs are fused.
Yes.
And what size fuses are you actually using?
2 amp.
Okay, but you could go up to?
You could go up to
10 amperes. Now, Eric, Dow Chemical. You guys don't use 16 gauge wire for controls.
Now, typically what we're going to do is all our starters are going to be pre-wired, and the only wiring that we run into is the external wiring.
And I'm talking about the control wiring. Are
Right.
you running separate overcurrent protection for separate control wires? Because that's
No,
a topic
because-
right now. That's
no.
a topic right now. So
Right.
we're not doing it. All right. So you are, but if you ran larger conductors, and if we went with this scenario where you have separate overcurrent protection for the control circuit, then you'd go to table 31016. Now, for you, Dan, that's pretty common because using PLCs, you're running separate protection. You get them down to 2 amperes running 16 gauge wire. Eric, you're not having separate overcurrent protection. Let's go to the second one. Common control circuits. A common control circuit isn't considered a branch circuit. Therefore, it has either supplementary protection devices, which would be like a fuse block, or the motor's protection device is used to protect the control circuit. Let's take a look at this here. Where we're making a connection and we're making a tap off of the circuit conductors themselves. Is that what you do a lot?
Yes, that's what we use.
All right, let's take a look at this example here. So this already pre-wired. Line 2 picks up one side of the coil, and then we pick off a line 1 with our 3-wire, in this case, our example 3-wire control circuit. This one has no overcurrent protection. And if we go to table 43072B column B, let's go to the code. Now we have to move over to column B. Column B says provided by, let me see if I can get a little bit closer here. Provided by the motor branch circuit protection. So column B says that, well, we can't see the wire size, so I'm going to have to kind of go back over here. But column B is conductors within the enclosure. Let's take a look at our graphic. These conductors, because of the shading, Mike's made it real clear that these conductors, the control conductors, are contained within that particular enclosure. So now, column B says protection provided by the motor branch circuit. Column B, conductors within the enclosure. And what size wires do you run, Eric?
Well, if they're
Control.
within the enclosure, they're by the manufacturer.
Ah, you know what? I'm glad you said that. If they're within the enclosure, the start-stop button is part of the controller, the assembly. Column B applies, but since it's part of the enclosure, column B doesn't apply to us in the field because it's automatically done by the manufacturer. Can I do that with column B, guys? Can I cross out column B? Everybody accept that? All right. And we got 18, 16, and 14. So when I kind of move this over, let's go to conductors that extend beyond 18, 16, 14, etc. So let's see if we have a slide next. So that one is column B, done by the manufacturer. Overcurrent protection for a common control circuit is based on whether the control circuit stays within or extends beyond the motor control equipment enclosure. Let's take a look at that code. Remember that. You had it extending, which is going to be column C, and then within is column B. Now, column B, if it's within, we don't worry about it. If it extends, we do. In some cases, the branch circuit, short circuit, and ground fault protection device for the motor is permitted to protect the common control circuit. Now, I said this, or I implied this, but I really like to take a look at this graphic. What we're saying is this. You have a 100-amp breaker. You have 8-gauge wire. We have no overcurrent protection for these conductors. And there are cases where we then can allow us to use the branch circuit protection to protect these conductors, as long as these conductors have a given size. And that's where 43072 is. If you have 18-gauge wire, then you can, 18-gauge wire, then the manufacturer would be able to tap off of a controller circuit as long as this device didn't exceed how many amperes? If it was a column B, that was 18-gauge wire, what would it be?
25 amps.
So this would be a maximum 25. And if they had a starter that had 16-gauge wire, well, then the maximum branch circuit that it could be connected to up here would be 40 amp. And 100 amp would be good for 14-gauge wire. But if we are extending it beyond, then you can see that it's 7, 10, 45, 60, and 90, which we'll talk about. So we can use the branch circuit protection device to serve as the protection of the control circuits, depending upon the size of the conductor and the size of the conductor relative to the size of the protection and whether or not the conductors leave the enclosure or whether they stay in the enclosure. We're not going to deal with staying in the enclosure. We're going to deal with when they extend beyond the enclosure. And that was the part about within the enclosure is column B. And we're not going to worry about the conditions of those numbers because we've already seen that here on table 43072B, dealing with the 18 gauge wire, 25 amps we just talked about, the 16 gauge wire, 40 amperes. Now, if the control conductors leave the motor control equipment enclosure and are routed to other equipment, then the motor branch circuit ground fault protection device cannot exceed the values given in column C. So let's take a look at that example. So 18, 16, 14, 12, 10. Got to move this baby over here. So if I'm going to be using 18 gauge wire, the maximum the branch circuit protection device could be for the motor, short circuit ground fault, is 7. 16 gauge wire is maximum 10. But if I then go to a 14 gauge wire, I could use 45 amp branch circuit protection for the motor. If I had a 12 gauge wire, I could use those conductors. So a 12 gauge wire is only good where the branch circuit short circuit protection does not exceed 60 amperes if I extend this out. Now, what size wire do you use, Eric, for your controls typically?
Well, Mike, I hasten to reiterate that this is for tapped control conductors that are directly off the branch circuit.
And I'm glad you brought that up. We're not talking about a fuse protection. We're just saying,
Right.
hey, listen, you're tapping off of control conductors, and there is no overcurrent protection for those tap conductors. You're using the branch circuit, short circuit, ground fault protection device to protect those
Right.
tap conductors. So therefore, there's a limitation on the tap conductors. Do you typically provide protection of your tap conductors?
Well, we don't have tap conductors per se because we have 480 volt motors and our control conductors come through a transformer. So it's a different section.
All right, so then right now we're not going to get involved in
Right.
what you're doing. Okay. So now we are making an extension away from it, but if I want to use 16 or 18 gauge control wire, and the tap that I'm making here is going to be exceeding the values given on this particular table. Let's say I want to use 16 and 18. Obviously, it's only 7 or 10. Then what I'm going to have to do, put a fuse block in there, provide overcurrent protection for those conductors. Dan, or any of you guys, is it common to make a tap and not have direct overcurrent protection for the control wires, extending beyond the enclosure? Or is the practice, well, let's put it this way, hold that. If you're going to do that, you're pretty much limited to some pretty small circuits, right?
Right.
A 40 amp protection device, a 60 amp, that's for 14, 60 amp is going to be for 12. You're probably not going to be running 10 gauge control. So more than likely, in some very small circuits, you'd be able to make your connection, make a tap, and take off. Is that pretty much there? So, but if we're going to get larger than smaller circuits, you need to provide overcurrent protection for those conductors. Then we'd have to go with a fuse block and provide a protection. That's if it's no transformer involved. Let's take a look here. Fusing, all right? Here is fusing of the circuit, and we're making a connection to it. And the fusing would be on both phases if it's going to be a 240 volt or line to line. We're going to provide fuses back here. Since this is going to be line 1 and line 2, we're going to have a fuse for each of the phases. And if it's a 120 volt circuit, we just fuse one phase. Control transfer protection. Now, this is, Eric, where you have a lot of transformers. Now, let's talk about that. Control circuit transformers typically have a single phase, 2-wire primary, and a 2-wire secondary. Now, before I get into this, I'm making some assumptions. I'm assuming you understand what a 2-wire primary is and what a 2-wire secondary is. If not, I hate to do this. I'm not trying to sell you theory. I'm saying, you know, you really need theory. And one of the things I've learned, and I teach it, and I preach this, you want to do theory before you do any course of ours. I don't care what you do. You need to have the fundamentals of theory because it is used in every course. If you're taking a grounding and bonding class, I'm going to tell you, you need to go take the theory course. If you're going to go to a national electrical code class I'm talking about, I'm going to tell you, you need to make sure you get an electrical theory class. If you're covering electrical calculations, I'm going to tell you, you need to complete the electrical theory class we have because it is the foundation of everything. You guys feel the same way about that? That you need to have those foundations. With not, you know, you're just struggling and things just don't seem to fit. And when you do have that fundamentals, it's like, I understand what that means and why that. Now I understand why the instructor was trying to, why it was so important to get those series circuits and parallel circuits and Ohm's law and all these crazy things. It seems like it makes no sense. It is absolutely critical. All right, so we assume you understand transformers, primaries and secondaries and common magnetic couplings and how the whole thing works. Here we go. Overcurrent protection is always required on the primary side of a transformer. Primary protection can be provided by the requirements of Table 450.3b. Now that reference is from the 430.72c2. Let's go to the code book, 430.72c2. Having to do with, let's go 72c. 72c is control circuit transformers. Then we go to number 2, complies with Article 450, and it references 450.3. And when we go to 450.3, A is over 600 volts, which we're not dealing with, and B is 600 volts nominal or less, which we are, then there's a table that tells you how to provide protection for transformers. Let's go with method number 1. Overcurrent protection isn't required on the secondary side of a controlled transformer if the requirements of 430.72b exception 2 are met. Well, let's go back to 430.72b exception 2. Conductor supplied by the secondary side of a single-phase transformer having only a 2-wire single-phase secondary shall be permitted to be protected by overcurrent protection provided on the primary side. I'm not going to get into any more details than that. And that is this. Your primary overcurrent protection can be used to provide overcurrent protection for the secondary, as long as it's a 2-wire primary and it is a 2-wire, actually, as long as it's a 2-wire secondary is the only critical thing, without getting into the details as to why. 2-wire primary and a 2-wire secondary. And you can get into the code book, and it has to do with a ratio and how this is going to work out, which I think is beyond the scope right now, unless you guys think we should talk about that ratio. Okay, just simply that primary protection. Now, Eric, use our example. You get your 40, is it 40 to 120 that you're dropping down?
Yes.
Is the transfer part of the assembly?
Yes.
Is there fuses automatically built within the equipment?
There are.
And so really you're coming off of X1 and X2, 120 volt control circuit.
Correct.
So we don't have to get into all the sizing and all the details here because we want to understand that the secondary conductors are considered protected by the primary protection device. Do you have secondary protection or no in that?
We do have secondary protection, but by the same token, these are motor starters that are built by manufacturers, and so they're products.
Right. And we don't. Okay. All right. Let me see if I can give a summary here because this is like, what's going on? I like to distill this down to what do I need to know as an electrician? Just cut it all off. Here's the deal. If you have a motor circuit and the motor branch circuit short circuit protection device going to table 430.72 isn't beyond 60 amps, then you could make a tap off of the motor branch circuit conductors and you could use 12 gauge wire. Okay, I can say I got a circuit conductors right there. I can just tap off of my motor circuit control and 12 gauge wire and I'd be up to 60 amps. Hey, once you get past a 60 amp branch circuit short circuit protection device, well, now you're going to have overcurrent protection for those conductors, and there's a couple ways to do it. One, run a separate circuit, take it to the panel, get your own control wires, provide the overcurrent protection according to Table 310.16. Probably, what's the largest wire, Eric, that you guys are using? 12 on a general. All right. Well, if 12, but Dan, you're using 16 because you have the overcurrent protection set at 2, but it could have been up to 10.
Well, that's on the outputs. The inputs, we actually group them and put them on 10 amp.
Okay, all right. But if I ran 12 gauge wire, put it on a 20 amp breaker, and then I can take off and do whatever I want to do. Or I can go ahead and make a connection by equipment that already had that has fuse blocks in it, and just put the overcurrent protection to provide it, or get a transformer, step down transformer assembly, and it's there. So as electricians, smaller circuits, 12 gauge wire, I'm going to be fine. If it's larger circuits, 12 gauge wire is going to be fine. I just have to make sure I provide the overcurrent protection of, let's say, a 20 amp protection device, and I'm set. Dennis, I know this was important that I cover this, and I don't want to blow it off anymore, and I don't want to, but is there anything you want to focus on making sure these guys understand about this part?
No, I mean, to me, this was kind of a key part because, you know, if they're pulling the wire and they get this given to them as a project, they just start scratching their head and they're going, well, do I, you know, like you said earlier, you got a 100 amp breaker, you're feeding the motor with number 8s. Do I pull number 8s to the start-stop station then? You know, how do I size that?
In your application, do you typically have taps to the controls, to the branch circuit conductors?
Same thing that these guys here are dealing with. You know, we're going to have a transformer in the MCC, and then just it's
All right, transformer
pre-wired.
MCC, it's already taken care of by the manufacturer.
Yep.
We're cool. Go 12
Yep.
gauge wire, you're good shape.
And
If
typically
you're
it's-
going to run your own control wire, then just put a separate overcurrent protection device of a 20 amp breaker, run 12 gauge wire, and you're going to be fine.
Correct. Correct.
Eric?
Mike, one of the reasons we run 12 gauge is simply for mechanical resiliency. Some of our motors are 600 to 1,000 feet from the motor control center, and so you have to pull that much wire, and it's just for mechanical sake.
And also voltage drop,
Right, voltage
which we're
drop
not
as
going to
well.
get into.
Right.
Good point. All right. Well, that's kind of okay, kind of a tough little unit there. Make sure you take a look at that in the textbook and review that. That's NEC stuff. Let's go to unit number 9. Indicator lights and illuminated push buttons. This unit covers the use of pilot lights and illuminated push buttons that indicate the status of a motor or associated equipment. All right, we got a pilot light, basically a lamp, internal lamp. We know we can change the color of this lamp. Is that right, guys? You told me that yesterday. The push buttons, we can make it a red, a blue, a green, yellow, whatever we want to. So, you know, there's, oh yeah, Steve has those little buttons right there. So we have that option there to kind of make that. And so,
You just change these lens out.
and here's just the symbols, right? And here are just the symbols that you can use. Here's just a green pilot light. Here's, I guess, a pilot light being supplied by a transformer, right? Reduced voltage, and I guess some have resistors and some kind of added safety features, which I don't care about right now. We just know that these are pilot lights, and they are different symbols, and they have different applications. Now, Dan, you told me about some pilot lights, some experiences in what you guys do with the pilot lights. So I think it's a good time to talk about that.
Well,
About-
the pilot lights that we generally use have the transformer type, and the bulbs that a lot of the transformers use are 6.3 volt.
Hold on.
So they're-
So you get a 120 volt circuit going to, is that the one right there?
Yes, this
All
is
right, we'll
one
see if
right
you can
here.
zoom in that. That's a 120 volt circuit, and there's a transformer built into that specific pilot light that drops that voltage from 120 to what?
6.3 volt, or 6 volt
6 volts.
nominal. Yeah, you have the contacts down here. This part is actually the transformer.
So you have a
part.
transformer, you have a 120 to 6 point. What the heck would you put a transformer to a stupid little pilot light?
What we do that for a lot is because if you use a normal incandescent bulb at 120 volt,
Okay, yeah, makes sense
and
to
that
me.
shorts or it burns out, the filament in there is likely to short circuit and really raise your current on
Hold
that.
on. You're saying
And
if you
if-
ran, hold on, I'm saying you're saying you got a 120 volt circuit, you got a light bulb. There's a short circuit, and we are on a control transformer, right? Or no, you're on a programmable controller in your particular case, right?
Yes.
So when it short circuits, the bulb burns out, it short circuits, now it draws a lot more current than it would have with the element being high resistive. What's the effect of that?
Well, since we use solid state outputs and have them fused at 2 amps, then you'll blow the fuse.
Oh, right.
And that's not a desirable effect. If you have it through the transformer,
Hold
though, you
on.
won't have that.
So if I blow the fuse, I'm blowing the fuse to the control circuit.
Yes.
So here I have a control circuit with a light bulb. The light bulb burns out. Now I drop out the whole assembly, whatever that whole process was, just simply because of a failure of a light bulb.
Yes, that can happen.
So by having a transformer, if the light bulb, okay, what happens if the light bulb shorts out in the transformer?
You don't get that much current on the 120 volt side of it.
Oh,
It's only
because
the
we've,
6.3
yeah,
volt.
yeah, because we've dropped down that energy. We dropped it down. Okay. All right, so now we know why they have light bulbs with this symbol right here. There's obviously a special application that people have solved the problem that they had with that. Connecting light bulbs for full voltage. Most pilot lights operate at full voltage of the control circuit connected between line 1 and line 2. Just, if you push this button here and you're on line 1, right there, it gets 120 volts and it works. I'm just trying to show you how a light bulb works. It's, nothing big deal there. Yeah, let's say application here. All right. All right, I got line 1, I got line 2. I have voltage on this side all the way to this side. So I have voltage on one side of the coil. I have voltage on one side of the light. I have, probably should shade this. I have voltage up to here, through the stop button. Voltage stops over here. And this is normally open, so that's it. All right, let's see what happens. If I press the start button right here, I like this better. If I press the start button, I get voltage to the coil. I energize the coil. It closes its associated contacts, which is the M contacts, the holding contacts, interlocking contacts, the latching contacts, the securing contacts, whatever you want to call this. It's closing the main contacts that we're not seeing to the motor, right? The motor runs. And because this auxiliary contact right here is being held closed by the M coil by pressing the start button. Okay, here's the voltages. Okay, here's the voltages. Okay, if I press this button, okay, it was pressed, it's energized, it's closed, it now remains energized. So now the light shows green. And basically, if you put your lights in parallel with your coil, then when the coil is energized, since the light is in parallel with the coil, it will receive the same voltage, right? Laws of parallel. Then, in this case, we're using a green light saying, yes, the motor's running. Hey, lights, do they use lights? Is there certain colors that use lights? Does green mean it's safe? Let me see. Green is safe. No, green means the motor's running. Red means it's not safe. No, red means the motor's... I'm missing something there. I'm confused.
I think we're all missing something, Mike, because in our case, red means danger, the motor's running. Green means it's okay, the motor's stopped.
Okay, so what color should this be? Is this the wrong color in this graphic? What is it standard practice in the field?
It depends on the engineer or the architect. It really does.
Really?
And the
Does,
client. Yeah, it really does.
So it could be green one time saying the motor's running.
It could be green saying the motor's running. It could be green saying that the control circuit is energized.
And it could be red saying that the motor's running
Exactly.
because it's danger.
I just hope that the same people who do the electrical stuff don't start doing traffic lights.
You know what's cool with traffic lights? They use what? A red wire for the red light? A green wire for the green light, a yellow wire for the yellow light. Those guys got it together. They must say, listen, we don't want anything to do with you electrical color coding guys and your lights configurations. All right, at least I know I'm not crazy about the lights here. So it could be any color you want to. It's up to the designer how you're going to do it. And I guess different people feel different ways. Men, they feel different ways at different days. One day it's a green, one day it's a red. All right, we'll move on. All right, let's take a look at this one here. All right, here is our... Here's our points. Okay, let's see. Here's one comes in to the stop. Okay, one comes in to the stop, and that's closed. Okay, that's closed. And then it goes over to a start. So from stop to start, okay, start. Start is open. Okay, that's open. We don't see the auxiliary contacts here. And then from start, it goes over to the coil, which we're not seeing. That's going to be over there. But then this one goes to the green light. So this green light is going to be in parallel. And, of course, here's the indicating contacts right here as well. So you have to play with this. I'm going to be honest with you. Even everything we're covering, and I told you yesterday, hey, listen, I'm not a motor control guy here. I'm just a facilitator here. I'm as confused as probably most of you guys watching this DVD. What I'm talking about, I'm confused. I'd have to take this, and Eric, you said it yesterday, I'd have to get a continuity meter. I'd have to, and Dan, like you said, you need practice here. I need to be able to draw this out. I need to be able to see the button. I need to get to the contactor. I need to mess with this thing a little bit. And it just takes me a couple times I got it. And then I might have to make little notes for myself so that if I had to go back to it again, I could see that. So those of you that are watching this, please feel comfortable that when you sit down for the first time that you're going to be uncomfortable and I got to just take some time And you know, as I was thinking about this as electricians and as myself as an electrician, I have a tendency to overstate my experience when I was an electrician so that I could get a little bit more money and I could get the next job. And I got fired because I couldn't hook up a 2-stage thermostat after 4 hours. You know, you're placed sometimes in a situation under a lot of pressure. So even though you finish this course, if you're going to get into some kind of control circuit, you need to have a little quiet time. You need to be able to just look at this, get the components, and if somebody tries to intimidate you, you know, you're going to have to just take the baloney from the guys and just say, hey, listen, you must be a brilliant guy, you understand this, but you know what? I'm still working on this. I'm still trying to learn. I mean, if you don't want to give me a break, that's okay, but I just need a little bit of quiet time. So give yourself a little bit of a break that you're going to have experience. This is not something you can just look at here without getting to it. All right, let's go on here. All right, what do we got here? All right. I like this diagram better. Okay, I got to stop, start. Okay, press the start button, energize coil, close and hold the contacts, keeps that energized. Oh, 1 second, hold on. Right now, my red light is on. The way the circuit is drawn, because it's shown a de-energized state, the red light is on, indicating that there is power, I guess is what they want to say. And then if I press the start button, energize the coil, close the M contacts that were open the M contacts that were closed, now the red light goes off. So let me see the logic there.
So the red would indicate stop.
Okay, red indicates stop. And when you press the button, the light goes off, indicates either the motor's running or the bulb is burnt out.
Or power failure.
Oh, power failure. There you go. Hey, is the motor running? Yep. Well, how come we got no power in the building? Well, the bulb's out. Motor must be running. Isn't it right? I mean, so I'm not quite sure if that's the best design to indicate whether the motor is running or not. But whatever. We'll go with what we got here. All right, what do we got here? Oh, here we go. Here's that picture again. All right. We can see voltage to the light. Red light is on. Press the start button. It closes the M contacts that were open, the auxiliary contacts, and then we had what? Auxiliary contacts that were closed, the 4 and 5. That'll get open. Light goes off. Indicates motor's running. We're in good shape. I love that design. That's a great one. All right. And where do you locate the pilot light? Of course. Oh, let's see the wiring. The wiring of the pilot light is going to be coming from the contactor, going back to the contactor in parallel to the M coil. So right here, I'd run how many wires up here? Just 2 wires. And it doesn't matter if this is a 1/4 mile away. It's just 2 wires to turn on that light that gets in parallel with the coil. So the key here is get parallel with the coil. Don't ever make a critical determination that a motor is running or not running based only on the status of the pilot light or illuminated push button. And we just saw that one example that's like, okay, the bulb is not on, indicates the motor is running, there's no power to the building, or there's no power to the circuit. You know, is that good enough information for you? Can you make a decision off of that information? So right there you can see, and I'm sure we can come up with another scenario, well, motor is not running, but in reality the bulb is out, the motor is running.
Well, even to go one step further, you could have absolutely no control power whatsoever, and your contacts could be welded shut.
Oh, yeah, let's talk
And
about that.
so-
Hold on. Say that. You say it because it's just intuitive to you.
Right, well, let's say a motor's running, and you go to turn the motor off.
Okay?
Well, if the contacts of the contactor have been welded shut
Now, the contacts is what get brought in when you energize your coil.
for the brand, right?
You energize the coil, wham! It brings it in and makes the contacts. And you're saying, okay, you turn it off. But the contacts don't release because they're welded shut.
Right.
Why would contacts weld shut?
Well, if you've got a lot of arcing, you could have some metal actually fusing and welding together.
So is that, I won't say common, but is that common?
It happens enough times that you better be careful.
In other words, all it takes is one time to get killed. That's how common it had to be.
Exactly.
In other words, if it welds shut, you press the stop button, but the contacts are still closed. But hold on. But if that were the case, using this previous example, if I press the start button, I energize the coil, right? I now close the contacts. The motor is running. I press the stop button. I de-energize the coil. The light then comes back on, right? Indicating the motor has stopped, but in reality, the motor is still running.
That can happen, yes.
You guys, right? And that's the danger that we're saying. You got to be careful. You can't depend on lights to tell you whether something is operating or not operating. But I guess we could use other controls, and that's where you could put something for centrifugal, voltage. Is there any voltage physically at the motor? Is there any current being drawn by the motor? Is it moving fluids? Is there something happening? You can actually tell, yes, that motor is energized or de-energized. Or is there no fail-safe? You need to go there, turn it off, lock it, tag it, then open it up with the proper protective equipment and find out whether it's off.
Exactly.
There's no other way, and even that people get killed on.
Right.
Okay. All right. I am done with the push buttons and the lights, rather. And we're moving on to Unit 10. Selector switches and truth tables. A selector switch is rotated by hand or key rather than being pushed and have 2 or 3 possible positions. I got a little one right here. Here is my push button. Press it down. Here's a push button, press it down. That's not a selector switch. Here's one that says one position, here's another position, and there's another. So there's a selector. You can select the type of switch condition that you want to go to. And here's another one down at the bottom here. So you have the push button, then you have the selector switch that's going to change conditions. That's what we're talking about right now. Truth tables. Truth tables or target tables are used to indicate the functions performed by different selector switch settings. All right, this is a truth table. We'll talk about that in a second. But let's just take a look at this selector switch. Here are the symbols. There's an A, which shows in the J position or the K position. J, in this case, happens to be identified as jog. K happens to be identified, as run. I would think J would be jog, but we're not going to go there. Okay, J is run, K is jog. That the A1 contacts in the J position is closed. If you go into the K position, you turn the selector switch to the other, right here, take a look right here. So let's say that was in the J position, I turned it to the left. That's going to give me a set of conditions. Let's take a look at that. In the J position, A1 contacts are closed, A2 contacts are open. Then if I take the same exact switch and I go in the other direction, that's going to put us in the K position. That means that A1 contacts now will be open and the A2 contacts will be closed. Let's kind of put this together in an actual circuit. I love our 3-wire control circuit now. I feel comfortable. I'm not as tired as I was yesterday with them. All right. Let's say we are in the J position. And in the J position, it indicates that A1 is closed. We can visualize that. We can see that. So if I press the start button, I energize the M coil, which closes the M contacts, which then is going to lock the M coil in. Main contacts close. The overloads are not open. The motor runs. The main contacts are not being shown. Everybody with me there? So now, how do you stop this? Press the stop button, and then, of course, you have to start it again. That is in the run position. And that's what we just did. That was the run. I'm sorry. Here's the run. Run position, press the start button, energize. It keeps the contacts closed. So coil is energized. Let's go into the jog position. Well, in the jog position, the A2 contacts are closed, but the A1 contacts are open. Now, you take your start button, and when you press the start button, do I have a sequence here? If I press the start button, while I'm pressing the start button, I'm energizing the M coil, and the motor, of course, the contacts are being closed, but the moment that I release the start button, because I cannot maintain the interlock or the latching contact here because I've opened it because it's in the jog mode, this motor then could only run when I press the start button, but the moment I release it, then the motor stops. So you just kind of tap it. So you go to start, it closes the contacts, it goes in the A1 position close, press the start, it runs. You go into the jog mode, which was the different condition. You press the start button, it runs. You release it, it stops. So here you're able to take a switch and create 2 different conditions. Now let's see if we can take a look at the actual truth tables. Under the J position, A1 contacts are closed. J position, A1 contacts are closed. And that's a number 1. And what the number 1 means, it means true. Are these contacts closed? And the answer is yes. Or you could put a check mark there saying, well, the contacts are closed. Now, it doesn't have to be J and a K. It could be whatever. It could be a 1 and a 2, right? I mean, it could be whatever the selector switch is identified, and they'll give you a truth table with it so you know, okay, well, under this condition, these A1 contacts are closed. But if you go to the K position, well, then A1 contacts are not closed, but they're open, but the A2 contacts are closed. Now, we had some discussion about this in our break time, and Steve, I think you said something about the shelf life, or one of you guys talked about why we have a truth table.
Well, as far as a truth table, it helps you to determine which position that switch is going to be in and what kind of continuity you're going to have, because some of these can get a lot more complicated than the one that we're looking at here, where you can have a lot of different functions and so on. But that truth table comes from Boolean logic, which led into digital logic with your ones and zeros, one meaning on and zero off. In this context, maybe we just think of it as a switching chart. It might be a little bit easier to really assimilate that.
See, it doesn't come, it isn't like it's a normally closed contact, which is normally closed, and so there's your symbol, so it's a done deal. No, because it's not normally closed, it's not normally open. I mean, well, how did you set your switch? And then that affects how the other switches are going to react and how they're going to respond.
Yeah.
And how did you change it again? Well, if you changed it again, well, now we have a different set of conditions. We got to know, okay, well, in this setting, what are the conditions of the switches? And I think, Dan, you were saying that these switches might have normally closed contact symbols shown on it. What were you saying about that?
Yeah, that was the point that I wanted to make, that the truth table will tell you which contact it is, but don't get confused with the normally open or normally closed,
That's shown on the physical device.
because that might just be the contact block that they had to use
Oh.
to get you to that position.
So they use a contact block, they put it together, that's already pre-assembled, that's a normally closed contact.
Yes,
But when they put it under a selector switch, depending upon how the switch setting is used, that normally closed contact under that setting might be open.
that's exactly right.
Or it
yes.
might be closed. So
Yes.
you can't be looking at contacts. You have to get with the truth table to find out in condition 1 or condition 2 or J or K or whatever manufacturer identification is, how is the setting going to be? And with that, then you're able to proceed forward.
And
Let's
the
go.
2 or 3 positions are pretty easy to learn, but they can be up to, 6, 7, 8 different selections, and that's when the truth tables really are needed.
Okay, and then
So
Eric.
the more complicated
So
they
as
get.
you were saying, different lengths. I mean, this thing.
Right, and also you also have on many of these switches 2 different sides. And so what'll happen is maybe you have one contact block white and a contact block red, or whatever the designations are. Well, J might have one function for one contact block, but a totally different function for the other one. And so if you're going to work with switches like this, really what you need to do is find some quiet place, some quiet time, sit down with your book and figure it all out and make it fit your application.
But I'm an electrician, so I always look at everything as an electrician. Aren't you going to give me this switch? I mean, am I supposed to figure out what switch I'm supposed to use? I mean, Dan, do you got to figure out what switch you're going to use to accomplish, or somebody's doing this design? Who needs to know about the selector switch? I mean, I'd just put a toggle switch on there and turn the stupid thing on. I'd be done. I mean, I don't care. But maybe you want more than just the motor running all the time. Who is determining what the needs are in designing the circuitry and telling me, use this switch? Because if you give me this switch and you tell me the colors of the wires and I understand what's going on, then I might have to go to the truth table or a continuity tester to figure out which one's going to be, and I'll make determinations. Or am I supposed to know that I need a selector switch? Who designs that?
Well, whoever designs the circuit is going to be the one that designs how many selections you need to be able to make.
Okay. So they're going to tell you what you need to use for that specific application. So Dennis, you're gonna as a contractor, you're buying this switch, you're putting those wires in there, and the guy's taking this switch here and he's gonna hook it up, but we need to make sure he knows how to hook it up.
Right.
He's not designing it. He's just simply, okay, you got a 4 selector in a 4 position, well then, 1 position, this is true false, this is making break contacts, okay, this one is this, so then you connect these wires here, boom, boom, boom. Okay.
Well, a lot of times that's the case, on new construction, you're going to have a print and a plan to work from, but a lot of times in the world for the small contractor, if you want to become the go-to guy,
Yep,
become
I knew you were
distinguished
going to
in
go
your
there.
field.
I could see that
If
coming.
you're going to be the guy that wants to be in the phone book, and they all look at, well, call Joe's Electric because he knows controls.
So he'll be able to hook up this press and this and this and
without the
this machine
plan,
tool
without the print, when
with-
they need it at midnight, that's the guy they're going to call.
All right, I can see where some guys love controls. I don't love controls. So I'm not the go-to guy. I'm going to say, call Steve Arn. He'll take care of you. Let him have fun wasting time as far as I'm concerned. All right, and I can appreciate that where it's going to. All right, let's go on. 3-position selector switches. Oh my gosh. All right, here we go. Okay, we have a JK and an L. All right, but it could be a 1, 2, and a 3, or 13, 14, and 15 maybe, or something like that. All right, let's take a look at this. All right, K means it is no contacts. J means A contacts are closed. K is no contacts. L means contacts 2 are closed. So I'm going to see if I can figure this out. So J is A would be check. And A2 is open. No jack. K, nothing. Neither one of them are going to be closed. That means closed. That means open. That means open. That means open. L, that means open on the L position, but A2 is going to be closed. I think I got it. All right, let's see if we can put this in use. Here's application. All right. Okay, hand, auto, off. In the hand position, the pump runs. Why would they say hand? Does that make any sense? How about just on?
Some people will call that manual.
Why
That's
manual?
real common to be on a pump circuit, to have a hand-off auto. That way, for testing, you could turn the motor on.
Okay, so if this was called manual, it makes sense to me because it actually has hand off auto. Manual means it's manually on,
Yeah.
right? I got that. And then it is off, which means there's no contacts being made, and then it's in the auto condition.
And in the auto position, you would probably use your float that you have pictured there.
So now, without getting in the circuit yet, if I'm in the hand
Hand-operated.
operated, in the manual mode, I'm obviously getting power from line 1 to my coil.
Right.
I'm bypassing all the controls. That's a two-wire control circuits, right? That's the one
Yeah,
right there,
exactly.
right? When I go to off, I'm basically having a stop button that's open. It's now complete. There's no power going anywhere.
Right.
When I go to auto,
You bring in all your control devices.
now I'm bringing in from the line 1, I'm now going to my 3-wire control circuit.
On your float switch.
Well, you're
Or
going
my
through float
float
switches,
switch.
temperature
I'm sorry.
switches, whatever.
I'm going to whatever the control
devices.
I determine it to be. So I could go to auto, but the motor might not start if it's a 3-wire control circuit,
Right.
which would require me then to go to the start button. And once I start it, it would run fine. But as soon as I lose power or I stop it, even in the auto mode, it's not going to automatically restart because it's the safety applications or whatever the other conditions were. I'm starting to get this stuff. I'm starting to like controls.
All right.
Yeah, that's what I'm talking about. I love controls. All right, let's go back to our graphic. All right. In the hand, which is, what did you say, Steve? That's hand-operated position, the pump runs. In the auto position, it only works when the liquid level changes. In this case, it happens to be a sump pump that as it comes up, it closes contacts, turn on the motor, then suck out the water. In the manual position, I'm taking line 1 directly to the coil. Bingo, energize the coil, close the main contacts, that motor is running. J, okay? If I go to K, well, nothing's going to happen now. It's not going to run. It's in the off position. If the float switch closes contacts, it's totally irrelevant here because I'm not going to get voltage to this side of the coil. Therefore, that motor is not running, right?
Right.
In the automatic mode. In the automatic mode, I go line 1 through the float switch. I energize the coil. I don't have holding contacts in this example because I don't need holding contacts because as long as that float switch is up, those contacts are closed, that motor, the coil is energized, main contacts are closed. As soon as the water level goes down, and then we had a differential, I think you guys told me about, right? There's a differential. How far does it go down? They'd go down a teaspoon and then go back up and down. Then it automatically opens up the circuit. So under the L position, it's in the automatic setting, and the J position was in the manual or hand position, and the K position was off. Okay, let's understand truth tables. So, in J position, A1 contacts are closed. K position, nothing is closed. L position, A2 contacts are closed. I got it. Variations for two-position selector switches. All right, here we go. Another variation of two-position selector switch is how the contacts represented in a control circuit. We have a single break symbol. We talked about that yesterday, Eric. You explained to me why maybe you'd have a single break versus a double break. And you were saying that, well, let's review this. What were the reasons why would I go with a single break selector switch versus a double break selector switch? I mean, aren't selector switches pretty much double break though? Would that be the general case? You go to J or K?
Well, they're really used for two different purposes. I mean, that a lot of the selector switches that switch power, like limit switches that actually switch power, they're going to be heavier duty, and a lot of those are double break. Dan brought
Hold on, slow it down. Heavier duty would be more than likely a greater ampere rating because they're distributing that energy and making and breaking over two contacts versus a single contact. So they might not be, okay, I got it.
But then, like I say, Dan brings up a good point in that if you have a double break switch, you can control two circuits. So you have one perspective, which is power handling.
Hold on 1 second. Right now with a single break, this is the only option I could possibly physically have, right, Dennis? Mm-hmm. I mean, this contact closes if you turn it to the left. This contact goes down to reverse, turn it to the right. Or a three-way switch, you go up, you go down. I mean, that's it. If you come down here now, you could have the break across the top. Okay, turn it to the left. And then if you go down the bottom, you'd have the contacts close across the top going to the left. And then the contacts in the bottom would close to the right. But you have the option to disconnect this jumper if you want to. And you can say, okay, well, this stays in here, disconnect the jumper, and have some other circuit that could be used, making and breaking with this portion here. Is that what we're talking about here?
Yes.
Yeah, I think what you see a lot of times, or what I see a lot of times, is a lot of these switches are double break, and a lot of the other electronic components are single break. Like relays tend to be single break, and a lot of selector switches tend to be double break.
Okay. We're going to go to the single break graphic. Let's just follow this here. All right, just a little practice here. Okay, we start. We energize power, stops on one side. We have line 2 going on the other side of the forward coil. Okay, here's a forward coil and a reversing coil. All right. If we take the selector switch, we put it to forward. When you press the start button, we're going to energize the forward coil, which will close the F3 contact. It will open the F7 contact. And we will have voltage that will travel and be held through to the F coil. The F contacts in the motor will be closed, and the motor will be running in the forward position. And because of the selector switch, you can't go reverse. If you want to go to reverse, however, you would switch the selector switch to the other position. It makes the contact on the reverse. And you would, oh, wait a minute now. You'd be able to go from forward, no. As soon as you open a contact to go down, you're de-energizing the F coil. You're opening up this F contact. As soon as you get down to the reversing position, that motor has stopped. Right. And we're talking, it stopped. There's time. You'd have to press the start button to get voltage across the start button to energize the R coil, to close, to keep that R contact open, and to close this R contact to interlock that. Right?
Right.
I got that one. All right, double. All right, what's the big deal, double? Okay, we have power coming in on one side. We have voltage on the other side. I press the start button while I'm in the top position, which is the forward position. I energize the coil. I close the F contact here that interlocks that coil. I open this contact that was closed on the de-energized state. I open that contact, so, well, it doesn't really matter. I couldn't go anyhow in that direction. So that really serves no purpose at all there. If I push it down to reverse, well, when I move it down to reverse, I de-energize this coil. I open up the F contact. I go into the reverse position. I have to press the start button to energize the reversing coil to close the reversing contact so that we can interlock or latch that reversing coil. And so it's the same, we're getting the same function, it's just that we're using a different selector switch, single versus a double break. Okay, chapter 2 is in the bag. Move into chapter 3. Many applications require motors to run both forward and backwards. And in this chapter, we're going to cover the concepts, components, and schematics necessary to achieve those goals, and that is to get the motors to reverse. Okay, starting at Unit 11, we're going to deal with reversing controls for three-phase motors. Let's just understand how three-phase motors operate. Line 1, line 2, and line 3, if we connect the T1, T2, and T3, then the motor goes in a particular direction. To reverse a three-phase motor, this is covered in a theory course, all you have to do is reverse any two leads. So if line 1 was connected to T1, but we now connect line 1 to T3, and if line 3 was connected to T3, but we reconnect it now to T1, and somehow achieve the reversing of two conductors, this motor will now run in reverse. But I have to ask you guys a question. I haven't done a whole lot of three-phase, obviously, in a long time, so I'm not an electrician anymore. I guess you are always an electrician. When you hook up a motor, does it always run the right direction? I mean, let's just start from the beginning. I mean, you got the thing hooked up, you put the three-phase conductors. Is there a direction that you really care anyhow? I mean, do you really care which way the motor starts and runs, but to get it to reverse the other direction?
If your line 1, line 2, and line 3 are correct,
Oh, wait, 1 second. Hey, it's black, red, blue.
yeah,
I mean, that's correct, man. That's line 1, line 2, line 3.
then most manufacturers will say that their motors, if you hook them up to line 1, 2, and 3,
Yeah, but
will-
how do I know what line 1, 2, and 3 is? I just put 3 wires out there, and the utility brought 3 wires, and they hooked up the 3 wires to my 3 wires. How do I know what line 1 and if the utilities give me power? How do I know what line 1 is? And Steve, you know what I'm talking about?
Yeah, Dan has the luxury of working at the same plant every day, where he knows what his system is.
All right, well, let's get you out of the
Those of us
picture
that-
then.
Yeah,
Let
those
me-
of us that are
Let's get with
contractors,
people
if
who
you're-
don't know.
If you're on a different job,
I go to
every
a
day,
warehouse, and I'm
Yeah.
hooking up a motor, and I
you're
just
a different
to the
job every
panel.
day. Yeah, you don't know.
Do I know?
you know, because there's a meter that will tell you.
Really?
You can buy a
Yeah.
phase,
Oh, okay. You're
a
saying
phase
Rotation
orientation
meter.
meter.
Okay, you're
Rotation
saying
meter.
you will know because you can get a little tiny thing that you hook up to line 1, 2, and 3. So what you need to do is if you have multiple three-phase motor in a facility, you need to make sure that the service conductors that you know, they're line 1, 2, and 3. Am I right about that?
Yeah.
So that everything else you connect to, if you use your color code properly, let's say black, red, blue, if that's the color you're using, then if you make sure you run line 1, line 2, line 3 to every single motor, connect T1, T2, T3, then they're all going to run the right direction the first time. But if you go to a warehouse, you get a three-phase motor comes in there, you run 3 conductors out there, you hop it on a three-phase breaker, you turn the thing on, and it's not running in the right direction. Well, I hooked up to line 1, line 2, line 3, but it really isn't line 1, line 2, line 3. You then have to then reverse those to get them to go in the forward direction before we start worrying about reversing it.
And that's why you never couple it to the driven equipment until you've tried that out to see which way it's going to turn.
Really? Okay, so you don't want the equipment already connected before you start the motor
Check your rotation.
because it could be bad news.
It could be.
So now, how much does it I guess it doesn't cost that much to buy a three-phase rotation meter, does it?
No.
What, $100, $200?
They're a couple $100.
Couple $100? But if you're going to be hooking up a motor, then, and if you're saying, well, but if you decouple it, right?
Yeah.
First of all, then you can hook the thing, all right, and turn the 2 leads, and now the motor's running in the right direction before we start reversing it.
That's
Derek?
a good.
Go ahead, Dan.
That's a good chance to use your jog push button because
Yeah.
if you hook it up,
You got a selector switch.
You got the
Put that
selector
baby
switch.
into jog.
put it in the jog, and
And
then
just
you
tap
can
it.
just bump it and see
Yeah.
which way it goes.
How do you know which way it's supposed? I'm like, I don't know. Is it going forward or backward? How do I know which way it's supposed to go?
Most devices that you hook to are either going to be a conveyor or will have an arrow.
So if the conveyor is going the
Like
other
if it's-
direction,
Like if it's a pump,
Yeah.
it'll have an arrow on it. Air compressors normally have an
Yeah.
arrow on them.
So is there an arrow on a motor that indicates which way the rotation is supposed to
Not on
go?
the motor, on the
No, not on the
equipment.
motor, but on the equipment that you're coupled to.
Hey, let me ask you a question. Is there supposed, if I go to, is there a direction that a motor turns? Do they go clockwise? Is that considered forward?
Well, that's an excellent question.
I thought so.
There are NEMA frame motors have got a bidirectional fan because motors have fans for cooling. And so if you have a bidirectional fan, then you can run the motor either direction. But on some of your larger motors, the fan is actually a unidirectional fan, and if you run it in the reverse direction, you would have to put a different fan.
But do motors, is there a standard direction that a motor is counterclockwise considered a forward direction?
Yes.
Because if that were the case, I don't need to have any meters. I go to a jog button, you know what I mean? I can just simply, okay, it's going counterclockwise. Okay, guess what? It's not going forward. So forward would be clockwise.
And it's from the front of the motor, which is the end opposite the shaft.
1 second. Which way am I looking at it?
Opposite the shaft.
I don't know what that means.
So wherever the shaft comes out of the motor, you're going to look at the opposite end.
So
For your
I'm
rotation.
standing here and the shaft is over there. I'm by here where the connections are being made to the motor.
Yeah.
And that's the direction that it goes. It rotates.
Counterclockwise
If you
It
connect
rotates
line one,
counterclockwise if
is
I'm
what,
behind.
is what they call standard rotation.
But if I go on the other side, I'm looking at the motor and I'm seeing the shaft coming to me. It goes which way?
Clockwise.
That's the side I want to go to. Okay, got it. All right. Hey, this is free. What are you planning on covering this in the DVD? So you guys got that one.
Can I just bring up one more thing?
Okay, fine.
Okay, thank you, Mike. If you have a facility that has several panels in it, then
Yeah.
your panels also have rotations.
What does that
So,
mean?
well, let's say your service has a L1, L2, L3 in sequence.
Yeah.
Okay. Well, if you connect up 3 wires to a sub panel, and those 3 wires are swapped,
Oh,
then you will have
Yeah.
a separate rotation. You might have a clockwise rotation on your bus of your service panel, but you might have a counterclockwise
so you're gonna have to change the
rotation.
2 wires. So you really need to make sure if you have Dan, you have a large facility. All your panels and all your phases are all line 1, line 2, and line 3. And you know when you connect the line 1, line 2, and line 3 to a motor, you know that the panel rotation, phase rotation is correct all the way down the line. True?
no.
Okay. But if it were true, then you wouldn't need a phase rotation meter and you could be okay. All right, let's go on. All right, you can see that, you know what? We better make sure we get the motor running in the right direction before we start so you don't screw everything up. And then we can start worrying about reversing this baby. All right, assuming we got the right rotation, line 1, line 2, line 3. And if I close the forward contacts, line 1 goes to T1, line 2 goes to T2, line 3 goes to T3. Motor goes in, don't tell me, clockwise rotation as I'm looking at the shaft. We can maybe put like a little round button there. I got that taken care of. Now, if I want to reverse the motor, I need to reverse any 2 leads. So line 1 now comes over. I go to the reversing contacts. It now causes that voltage to continue to T3. Line 2 goes to the reversing contact, which goes to T2. Didn't change. Line 3 goes to reversing contact, goes over to T1. I now connect line 1 to T3, line 2 to T2, line 3 to T1. Now we're going to have rotation opposite of the original rotation. Got it. Interlocking devices. Interlocking reversing controls prevent the forward and reversing contacts from being energized at the same time. A good plan. So, this is a mechanical interlock. We're not going to spend too much time here. But the way this interlock works is that if you press the forward button, then mechanically it disables the reversing contacts from physically being able to be closed. Is that right, guys?
Yes.
It's done mechanically. It's not done electrical. And if I'm going in reverse, well, then you can't press the forward button while you're going in reverse, because if you press the forward button, then the reverse button isn't going to work. Or it's going to take you out of reverse and it's going to go in a different. You can't have them all close at the same time. We don't want to go line 1 to T1 and then have line 3 go to T1 and then have them both close at all 6 contacts closing. So there's a mechanical connection to prevent them from all closing.
I think you could switch, but in
You
switching,
could switch.
It's going to remove. It's going to de-energize the opposite direction.
Right. So you're either going forward or you're going reverse, or you're going forward, reverse. But you can't go. You can't close all 6 contacts because 3 of them will close, and then mechanically disables the other 3, or the 3 here close and mechanically disables the other 3 contacts. Do we have a mechanical contactor there?
One right here,
Yeah,
where it shows it right here.
right there in the center of that particular one. There is a mechanical interlock physically right there. Okay, let's go on. Most reversing magnetic starters contain factory installed mechanical interlocks between the forward and reverse, and that's what you just showed there, Dennis. The interlock device physically locks out one contactor at the beginning of the start cycle for the other contactor. And that was that's a picture of the mechanical interlock, right? That's the dotted lines.
Yeah, here we have gone to electrically operated relays, though, and the picture we had before was a mechanically operated.
Oh, you're right. This
have
one
switched a little
was
bit.
a physical,
That was
no
totally
coils,
mechanical.
no electrical.
Yeah.
This one is going to be an electrical that went, okay, let's follow this one here. Let's see if we have it. There we go. We press the forward button, energize the forward coil, closes the F contacts, which keeps the F coil energized. The F contacts are all closed, motor runs forward. At the same time, the F coil, that's it. And because this coil is energized, it mechanically disables the reversing coil. Is that what it's doing? It prevents it from going in reverse.
There's a mechanism.
There's a physical mechanism that when this coil is energized, and then it physically can't go there. Let's go to the reversing button. You press the reversing button, you energize the reversing coil, and that then closes the reversing contacts, but mechanically. Tell me, I'm confused here. Is this forward and reversing button causing a mechanical disconnection between the 2 coils? Or is
There's just a mechanical arm between them that won't let them both pull in at the same time. And one of the dangers of this circuit, where it doesn't have any electrical interlocks but just mechanical, is you can push both those buttons at the same time, and it's going to try to energize both, but it mechanically can't. So you're going to sit there and fight, and you're going to burn out one of your coils.
So they're both trying to go
Yeah.
this way, but you press them both at the same time, and now you're creating it. You got something there,
Well,
Dennis?
this one here is the electronic, and I can push this one in here and try to push this one in, but it won't go. And then release this one, push this one in, and then this one won't go.
Oh, so there's a mechanical connection that
Right.
when that coil energizes, it kind of like drives something in there that prevents the
Yeah.
other one from mechanically making and breaking, because it's the contacts that's
There's a lever between them.
Ah, so when you energize this coil, it's making these contacts close, but it's mechanically then like putting a shim in, preventing the other physical contacts from contacting. But, as you said, Steve, if you press them both, then both coils are energized, and they're both trying to close. Got it. When this type of reversing controller is used, the stop button, push button, must be pushed to de-energize the contactor before the motor can be reversed, allowing the interlock lever to reset. Let's take a look at this graphic here. This is the mechanical interlock one. Here is our ladder diagram, and here's our wiring connections diagram. And I'm not going to get into all the details, but here is my forward contacts. Here's my reversing contacts. We already seen where line 1 goes to T1, and line 2 goes to T2, and line 3 goes to T3 if you have the forward contacts. And if you energize the reversing coil, then line 1 goes over to T3, line 3 goes over to T1, and depending upon which coil, there's a, now this one doesn't have, the mechanical interlock is shown here. Of course, it wouldn't be shown necessarily there. And we could then follow the wiring in here and house of control, say line 1 goes over to stop, but I'm not going to get into that details. You guys can take some time and kind of practice that. That's not the point we're making right now. How about we can add electrical interlocks for the magnetic reversing controls? Electrical interlocking is accomplished by wiring the auxiliary contacts of one circuit to control another circuit. All right, here we go. Okay, we have mechanical interlock so that if I energize this coil, there's something that's going to wedge that's going to prevent the R contacts from closing. We just don't see that physically now. So let me see if I have any sequencing here. I press the forward button, energize the F coil, which closes the F contact that was open. It opens the F contact that was closed, and it closes the forward contacts for that motor to operate forward. Steve?
So now I'm not going to be able to burn up my coil by pressing the reverse. I've taken that problem out.
So now, in this case here, if I'm pressing reverse, because this F contact that was closed is now open because the F coil is energized, I can't get voltage to this R coil.
Right.
In this one, if I had forward running, I could, at the same time, electrically press this button, and I could energize the coil.
Right.
It still might be running forward,
Yeah.
but it will be running forward because that was the first one we pressed. It interlocked the contacts out. It's not interlocking the coil, it's interlocking the contacts out, but this allows me to press the reversing coil at the same time the motor is running forward. If I'm running forward, then electrically we have disabled the control circuit to the reversing coil. And if I was running in reverse, the R coil opens the R contacts that were closed, closes the R contacts that were open, it latches the R coil, but if you press the forward button, you cannot energize the forward coil. Push button electrical interlock. 2 double circuit momentary contact push buttons provide the electrical interlocks in this control circuit. All right, what do we got here? All right, we have a forward button that has closed contacts and it has open contacts. And then we have a reversing button that has closed contacts and reversing button that has closed contacts and open contacts. And for a moment I was thinking, well, wait a minute now, isn't that a selector switch? And the difference between this button and a selector switch is that we can't change this condition, can we? These contacts are closed, and these contacts are open.
Well,
and there's
only
nothing.
momentarily.
Yeah, but I'm saying we can't change this ever so that it would be where that is closed
Right.
and that was open.
Right.
Correct.
All right, so we're not going to worry about that now. All right. Here is my normally open, normally closed contacts. Okay, that's right. One is closed, one is open. Here's a symbol and a ladder diagram. Now let's see what this means. Let's go with forward. Press the forward button. Oh, when I press the forward button, I am mechanically opening up this normally closed contact that's normally closed, so that if the coil R was energized, I'm going to de-energize the R coil, and I'm going to close the contact here that will energize the F coil, which closes the F contacts. At the same time, I have the F contacts here that close, that were open, and that latches that coil, so now I'm running forward. What we have here is we have the mechanical interlock, as well as now we have the push button that will disable one versus the other. We just don't have the F, we're not using auxiliary contacts. Where on this example here, we were using auxiliary contacts, is that right? Right here?
Yes.
To disable that control circuit, where in this one, we're just using a push button. And when you push the forward button at the same time, it's going to open up these contacts right here and disable the reversing coil. So there's,
Right.
there's ways of being able
Yeah.
to
Right.
provide a level of protection. And this one has both of them. You have the mechanical interlock, and you say, you know what, on top of that, I don't want these guys to press both of those. We're going to go ahead and do a push button interlock. Steve?
This one does a good job of protecting your starter so you can't energize both the forward and reverse. But the disadvantage is you can slam it right from forward into reverse just by pushing one button. And I think Dan can talk to what that does to equipment.
Hold on one second. If I press the forward button and I'm energizing the coil and I close the F contacts, that baby's running, right?
Yeah.
Right.
I could then immediately press the reversing button. Oh, no, I could press the reversing button, and immediately at that instant, I open up the voltage to that motor forward, the coil. But at the same instant, I'm also energizing the reversing contact.
Yeah.
So I'm going from forward
Slammed out.
immediately to reverse. It's like
Yeah.
driving forward and going wham into reverse.
Yeah, it's called a
Yeah, you can.
plugging
You're not going
reversal.
forward and reverse at the same time.
Right.
But I mean, you're trying to go in reverse. But what's the difference? What about
That's
the
called
other
a
ones?
plugging reversal when they do that.
But hold on, I want you to say that term. In this example here, even with the interlock, if I press forward, I energize the F coil, close the F contacts, I'm going forward.
Uh-huh.
If I can't press reverse.
Nothing will happen there.
Right.
I
That
have
locks
to
you out
press.
from reversing. You have to hit stop
I
to
have to
reverse.
press stop.
Yeah,
Then I have to. Okay. Then I can press reverse.
right.
Right.
And that action of hitting the stop button is probably going to take a second or two and let that motor coast down at least a little bit.
In other words, it's not wham.
It's not a plugging reversal.
You have to press stop. But maybe you don't want a motor that goes in reverse within a certain period of time. Is that right? That's when you put some other controls, some timing that
Yeah,
won't
it's real
allow
common
you.
to put a time delay in between a forward and reverse.
Yeah.
It really saves the motors. It's really hard on them to, because as we talked about before, you have 600% current when you start a motor. Well, if it's already going the wrong direction, you're going to have somewhat a lot more than that, maybe 1,000, 1,200%.
So if you're looking to now, what you could do is put some kind of device that would measure the rotation of that motor. That once it stopped turning, right? You could have
Yes.
a two-wire limit, right? Switch.
Yes.
So okay, the motor has stopped turning. Okay, now you can then go in reverse. So you can. That's where you start adding controls, as we're talking about. And that's when Steve said you become the go-to guy. You go out to this machine shop, and this guy wants this and this and this. I want to make sure you protect my motor. I don't want this motor to be able to go in reverse until after it stops. Well, then now you start designing the circuits and make it happen. All right, let's talk about combining interlock methods for a reversing starter. Reversing starters that combine all three types, mechanical, electrical, and electrical would have been what? The push button as well as the auxiliary contacts is the most common reversing starter design. All right, let's take a look at this here. All right, here's the mechanical, and Dennis, you had showed us the mechanical, the physical mechanical, and then we had gone over to where the auxiliary contacts, we're using F1 and R1. I like when we have an F1 and an R1 or F2. Those are nice. And then we have the push button that if you press the forward button, you close that one. Well, then you open up the close contacts of the forward button, which disables the reversing coil. I don't think there's a need. You guys want us to go through the whole thing, or you think it's kind of straightforward? And we cover the three different ones, and people can take a look at that if you're not sure. And we're going to cover it. Here we go. Let's see. Okay, right now in the stop position, the coils are not energized. We probably shouldn't color that one side right there. But if I press forward, I energize the forward coil. I then will close the F contact, and it'll latch that coil. I'll open up the F2 contact that was closed. That will then electrically disable that R coil, and we've mechanically disabled the R coil. And by pressing the forward button, we opened up the F contact that was closed so that if somehow the R coil were energized, as a third possibility that there's no way to energize that R coil. And that was our forward button, and we kind of got that taken care of. Motor continues to run forward. That's the example we just did. Let's take a look reverse. Okay, stop it. You got to stop it first because you can't go reverse. You stop it. Now, pressing the reverse button. Open up the reversing contacts that prevents the motor from running forward. Energizing the R coil, which opens up the R2 contacts, will now for sure disables the F coil. Also, there's a mechanical interlock that disables the contacts for the F coil to close. Then we close the R1 contacts, which interlock the R coil. And then when we release the button, the R coil is energized. The F coil contacts are disabled. The R2 contact is held open, disabling the F coil, and we're good to go. Wiring a reversing control with a selector switch. A two-position selector switch can be used with a regular start-stop push button station to control a reversing starter. All right, let's see what we got here. Two-position. Oh, I see, because we have a forward coil and we have a reversing coil. And if we go to the forward position, press the start button, energize the forward coil, close the F3 contact that was open, open the F7 contact or the F contact that was closed, so electrically disable the R coil. By F contact being closed, we probably don't need all these numbers on here. I don't think that adds any value, so we'll probably remove all those in these examples. by the F coil being contact being closed, we energize the we keep the F coil energized. All right, let's see what we got next. That was the start button, and what we just described. So that stays energized. Now, if we go in reverse, now guys, if we go in reverse, the moment I go to reverse, I de-energize the F coil, right? And I actually drop, then it goes into a de-energized state, doesn't it?
Mm-hmm.
This graphic really is only accurate that when you go into reversing, so we need to identify that this is only going in forward after you press the start button
Right.
because we're in the forward position. And this is only energized, and we need to make sure we make that clear, that if you go into the selector switch, the reverse button, close in these contacts down here, maybe the A2 contacts here get closed, but you had to press the start button, energize the R coil, open up the R contact, disable the F coil, close the R contact here, which interlocks the R coil. I can see a selector switch. So really what I'm learning here is with all the different combinations of switches, there's lots of ways of skinning this cat. Approaching the tools that you have. Okay, I can't get this working. Hey, put a three-way switch there.
Exactly.
Hey, you know what? We could use this. Let's put a two selector switch. So the more knowledge you have, the better you are at solving these problems.
Mike, is that you have to understand what the functions of the motor is to be and how it's to be started and stopped and what other items are in there that's going to control the motor.
And
once you understand that, then you can pretty much use anything.
And as Steve said, the more you know, the more you can help your customer. You can say, you know what, we really should put something in here to prevent the motor from this, or we really should do this, we should look for this, and we should protect this, and we can add more features. And so that's the way, as a contractor, you're a contractor, that's the way for you to upsell, but you're really taking care of the customer's needs. If they're not providing, whoever designed the system is not, or you're designing the system. Reversing controls with limit switches for three-phase motors. This unit covers the use of limit switches in conjunction with other components to control the duration and the direction of motor operation. Another variation to the standard forward and reverse control circuit is the use of limit switches to automatically stop a motor when it's reached a predetermined amount of travel or torque. All right, let's take a look at here. Okay, I got my ladder diagram. I got my forward buttons. That's I think they were two position buttons that when I press the forward button here, I'll energize the F coil. I'll disable the reversing coil, so I have protection there. I got some mechanical interlock between the contacts of the forward and reversing. I got a green light in parallel with the forward coil, and I got a red light in parallel with the reversing coil. And then we have a forward limit switch that we can place in this portion of the circuit, and we have a reversing limit switch that can be placed between this portion of the circuit. Let's take a look at that. If we put the limit switch between 3 and 6 for forward limit switch and a limit switch between 5 and 7, all right, stop button is normally closed, reversing button, this portion is closed, this portion is open, this forward button is open, and if I press the forward button and the limit switch is closed, the forward limit switch is closed, and the forward coil will get energized, the green light will illuminate, the F contact that was open will close, this will interlock the F coil, the F contacts to the three-phase motor closes, the F2 contact opens, which provides protection against going in reverse. We have mechanical interlock, so the coil cannot close the contact simultaneously. We have this reverse button that's open, so therefore you can't energize. We have all our what? We have our button interlock, we have the electrical interlock, and we have the mechanical interlock that we talked previously. So if you press the forward button, motor's running forward. Let's go backward. In order for this to go reverse, if I press the reverse button, that will then de-energize the F coil, open up the F1 contact, close the F2 contact, but I can just about have this baby go immediately in reverse, can't I?
There's going to be a short break, but it will.
But
Yes.
yeah, for all practical purposes, this thing, it we. Oh, we didn't talk about, Dan. I wanted your feedback on that. Have you guys had any experience with a motor running in one direction and then immediately, that it goes in the opposite direction because of something
That's
like
on single-phase motors. If you reverse a single-phase motor before the centrifugal switch drops out, and we'll probably be getting into that later in this
Okay.
chapter.
All right, but what happens physically? Anybody know what happens when you take this motor that's running in one direction? You
Oh,
immediately.
You can tear them up, and depending on what kind of equipment you're running too.
I understand why if it's electrical, why are you? How can you tear up a motor? Is it pressure torquing?
the
It's
torque,
the
yeah.
energy. You have all this kinetic energy going one direction. Now electrically, you're twisting one while it's trying to twist the other. Is that
Yeah.
what's going on?
Yeah, it's not only locked rotor, but you're going the other direction, so you reverse, you're more current than locked rotor.
Oh, is that right?
Good example is a hand drill that's forward reversing. So you got it forward and you let your finger off the trigger and all of a sudden you throw it into reverse and hit it again. And I mean that torque, it just torques your hand back from it all of a sudden reversing. So you could just picture that on like a 25 or a 550 horsepower motor and see, see what
gotcha.
it's going to do.
Depends on the kind of equipment too. If you're driving a conveyor belt full of coal in one direction, once you slam it in reverse, all your inertia from all that weight, you're going to be breaking up all kinds of the equipment too, trying to reverse it.
Oh, as all this equipment that's being turned by the motor, which driving this inertia, all that equipment is attempting to go in the opposite direction while
Yeah.
we're having all that mass going in one direction. So now you wipe out all of this mechanical portion.
Yeah.
All right, excellent point. Again, if that's what you want, then looking at the circuit that we have here, this is not the best circuit. You need to put some kind of slow it down so you can't go immediately into reverse. All right, let's go on. Reversing controls, limit switches for automatic forward and reverse. When limit switches are used for automatic forward and reverse circuits on machinery, double circuit limit switches are generally used. All right, here's a double circuit limit switch. Now, this is not a selector switch. I don't have choices to change here. This is just the way it works. You have a set of normally closed, set of normally open contacts. Okay. So if you move the lever, okay, that's what it looks. You move the lever, okay, if that's normal position, that'll be closed, and that'll be open. Then you can turn it. That would open it, and that would close it. All right, let's take a look at this limit switch here. Okay, so this is closed, and this one would be open. If I press the start button, I energize the F coil, close the F1 contact, interlock the F coil, open the F2 contact, prevent this from going in reverse. This thing is going forward. When it gets to a certain predetermined point, this would rise, this would open, de-energize the F coil, open up the F1 contact, close the F2 contact. All of a sudden, when it gets to the end, oh no, as soon as it opened, it stopped the whole process, right? It
Well, that would-
stops.
That one on the bottom would close and that would energize your reverse.
Well, no, because when this open and then this goes to close, isn't there going to be a delay? So therefore, this coil will drop out?
Your forward will drop out and your reverse will pick up.
I thought I'd have to hit the end, it would stop, and I'd have to press the start button. Are these going to, is this going to make before this opens? Or are they going to
No,
do it at the
they're
same
gonna do it at
time?
the same time.
So you're saying the way this thing is shown here, this is going to go from forward. When it gets to the end and it opens, this is going to close, and it's not going to.
It has the potential, Mike.
Okay.
It
it
has
has-
the potential.
That it might close and go in reverse, and it might not,
Right.
because it's a matter of timing. Yes.
And that's another characteristic, not only of limit switches, but your push buttons, anything that has two contacts, is you need to know, are they a make before break or a break before make contact? Some of those are built with a differential in their switching, built
Okay.
right into them.
So, and we don't know what this is.
Yeah,
gonna
we don't
be.
know what this is.
All right. All right, let's see if we can look at an application. We have a conveyor, and we have this contact right now that's closed and that's open, and then this one else, limit switch 2, this is closed and open. And when we go this direction, it changes the state of that one that was closed, and the top one was closed and the bottom one was open. that this one is open and the bottom one is closed. And let's see if we go the other direction. We go the other direction, and when it hits this point, it went from open to closed and from closed to open. All right, let's take a look at an example here. Let's assume, okay, for the class, Dan, and for everybody else in the video, that these are making at the same time, okay? Let's go with that assumption. Go ahead and make an assumption. All right, here we go. We have the stop button. I press the start button. Coil F energized. F1 contact is closed. F2 contact is open. I mechanically interlock the R coil out. I electrically interlock the R coil out with the F coil F2 contact. F1 contact is closed. We can get rid of these numbers. They don't serve any purpose for this application. And I would then have voltage traveling on here. This coil is energized. But, so we're going forward. As soon as this hits this point right here, it now opens the L2. It will open this. It will close the limit switch 2. And if it happens at the same time, then we maintain voltage to the R coil because we de-energize the F coil. We close the F2 contact. And we close the that F2 contact that was being held open. We allow that to go back to its normal state, normally closed. Then the R coil is energized, which closes the R1 contact. And now we're running in reverse. Is that okay?
That's correct.
Let's go now in the reverse. Now it's running in reverse. So this thing is going back and forth. Give us an example where something would be up, back and forth, Dan.
Well, I'd give you a couple examples. One, the easiest would be like a stretch wrap machine where you've got a turntable that your pallet would be turning on, and then your stretch wrap, of course, is going to go up to a limit switch and then down to a limit switch. And however many wraps you put on it, that way it'll
Is that a
evenly be
manual thing that you
dispersed.
press it to hold it, or is that something that it could then determine? You could then put a counter, say how many times this thing is wrapping around it, and you can say 4 wraps, and that's another control. Is that right? Counter 1, 2,
Yes,
3, 4.
and you would use the limit switches to change the direction just exactly how you have it listed here.
Okay, so now we're going in reverse, and when it gets over here, okay, so now stop button. Okay, this was being closed, is what it was. Energize the R coil, but when it goes back, it opens up limit switch 1, closes limit switch 1, which then has it going, see, it's going up, and it's going forward, it's going backwards, forward, backward.
Yes, exactly.
Steve?
There's one spot in there that's a little bit difficult to visualize, and I don't know if I can help it by saying this or not, but when we first go through that and we say it's switching directions, we can get hung up thinking, well, when we go to reverse, that F2 contacts are open and they have to close. But we want to remember the LS2 contacts down there are not a momentary. They're going to remain closed as long as we're dwelling on that limit switch. If we're at the end of travel, LS2 will stay closed long enough to let us make that transition from forward to
This
reverse.
isn't a momentary thing that's occurring.
Yeah. Right.
We're talking about
As long
it
as our
hit
box, as long as our product is against it.
Dennis has it.
Okay, yeah.
So as soon as the product hits it, it held it. Now
holds it in
drops
this-
one out, okay, because it opened it.
Yeah.
But it closed a set of contacts, which puts the other one on.
Yeah.
So therefore, that's why it wasn't like a momentary,
Yeah.
contactor that was dropping one. It's a mechanical connection, and then all of a sudden, boom, it goes the other
Yeah,
direction.
we got to see that it stays closed long enough to let us make that transition.
That's the answer. That is perfect. Let's see what we got next here. Reversing controls for limit switches for garage door applications. Okay, that's kind of like makes sense here. All right, here's the control circuit, and here's the dotted line as an option that you can add to it. You get rid of the jumper between 3 and A, and you add the limit switch in between 5 and B. So 3 to A is you get rid of your jumper, and you can put the limit switch, and 5 to B is where the jumper can go in for a limit switch. And so we put the jumper between 3 to A. Oh, but this doesn't have the 2 switches. This only has 1. I think I know where this is leading up to. The other one with the 2 switches was leading up to what? It gets to the end, it stops, it rotates, it comes back the other direction because there's enough of a delay, and then it goes back and forth.
Yeah.
This one is a garage door. I'm not looking for it to go up and down, up and down. I'm looking for it to go and then stop. So I'm only going to use a single contact in limit switch 1 and a single contact limit switch 2. Let's see. I want the door to go up. I press the up button, energize the up coil, close the U1 contact that was open the U2 contact that was closed so I can then electrically interlock the down coil out as well as the mechanical interlock between the contacts. And then the U coil is energized, close the U contacts to the motor is going up. Then if I press the down button immediately, I can't, can I? I can't, I mean, I can, yeah. You can press the down button, but you can't energize the down coil because the U coil has electrically interlocked as well as mechanical interlock, so that's not going to happen. All right, let's look at the example here. All right, the energized state, the the up coil and the down coil has the voltage it needs from line 2. We have line 1 voltage coming in here to all the switches, is to all the contacts. Press the up button, energize the up coil. We're going to then close the U1 contacts, open the U2 contacts. We're running, and that's the state right there. Closes that, opens that there. And then you release it. It will continue to run until limit switch 1 opens. There must be a travel that it's going to go. It's going to hit a limit switch, and then it's going to open. That limit switch then will stay physically open. And now, so it's open. All right, so now that U1 contact will open that was being held closed, and the U2 contact that was closed was being held open, puts us to this state right here. Now the motor has stopped. Now, this contact probably is still open, isn't it?
Yes.
Yes.
So we'll probably have to show that graphic where that contact is still physically open because we are down, we are in the up position, and that limit switch 1, the limit switch up, is still open.
Right.
And we'll get that changed in the textbook. All right, let's now press the down button, energize the down coil because limit switch 2 is closed. And then press the down button, close the down contact 1, open up the closed contact D2, release the button. I'm able to maintain voltage to the down contact, so the motor is now going in the direction to go down. And once it gets to the end of travel, it has a limit switch that opens it, and now the door is down. I'll have to take a look at my limit switch at my house because I have a garage door that goes up and down. I'll have to take a look at that. Good stuff. All right, any comments on this one?
Well, the one thing that you may end up throwing into this is the photo eyes down at the base of the garage door.
So it might not be a physical limit switch. It might be, it would be a switch that's going to be
Well, I'm talking about
optical.
the emergency to
addition.
where
In
the little
addition.
kids go through and they're one of those, that'll
safety.
override everything, the safety
Hold
version on the eyes.
All right, I agree with that. Okay, so now, if I want to add, what's it, optical? I mean, what is that? It's
Those
an
would be
infrared?
optical, yeah.
Okay, so there's a beam.
Mm-hmm.
So if I hit the beam, that contact that contact would be closed, right? What causes that to open? What is that doing? Is that operating another coil?
Yeah, a little
You have a
relay.
2-pole switch, so it would do just like,
It would override everything
So
that you have.
right along here, I'd have another set. I'd have another set of contacts
Yeah.
with another coil. That when I energize that coil, I would open up the circuit coming to the control circuit and turn it off.
Actually, you reverse it because the photo
They go
eye
back
is
up.
only in the circuit when the garage door is coming down, and if something breaks the photo circuit, then the garage door immediately reverses.
Oh, you're right. We're not going to stop it. We want it to go back up. All right, help me out here. Down. When I push the down button, I energize this. I would then close a set of contacts that would be to the photo eye to activate that circuit, right? Because it only applies when the garage door is going down. Am I right about that?
Well, this is a good example of where you bring Dan in with his PLC. What's happened is in the old days, labor was expensive or labor was cheap and products were expensive. But now in today's age, labor's expensive and electronics has gotten cheaper. So a lot of these garage door openers don't have these limit switches per se anymore. They're all on electronic boards.
Okay.
In-
Yeah, we're not doing
Yeah.
this mechanical stuff anymore. It's all done with a processor.
Right.
And so it's using the electronic image. The concept is the same.
Exactly.
But except it's handling it with electronics. It noticed the infrared. It noticed a change in that signal. It knew it was going down, and that's what the programmable
Right.
controllers. Got it.
And this is where it's beneficial to go to the manufacturer's diagrams that they have, instead of just throwing them away like a typical electrician
Yeah.
does.
I definitely got
falls.
better reading instructions
Yeah.
as I've gotten older. There's no question there.
You could
All right.
add, the, like you were saying, to make it go up, but you'd have to use a 2-pole switch, and it would be just the same as your push button interlocks. So you would open one, or your limit switch
Yeah.
interlocks, where you open one and close the other
Right.
to make it go up.
So mechanically, we can get the parts to make it as it's going down. If you see the infrared, then activate something, and then have it go back up. In other words, it's just what Eric is saying. It's a lot of material here, a lot of labor, a lot of work to get something that the garage door opener guys have gotten down to electronics. All right, let's go on. Make a diagram. It can be helpful for the installer to make his or her own riser diagram to help lay out the job. Well, here's an example that if you were going to be using the limit switch down, the limit switch up, and you start push button, you kind of like hand draw this thing out and get your wiring and say, okay, now I know what I'm running and when I'm running, and that's what I did when I pull wire. I just knew what I was doing in advance, and you just pull it in there, and then you make your terminations, and then you take one stage at a time. All right, we're done with unit 13. We're going to unit 14, and maybe these unit numbers are not exactly the same because in case we decide to move something after this recording, and that's a possibility. So if I set a unit number, and well, that's not the same in the book, just not that big of a deal. Reversing single-phase motors. The most common type of motors used for single-phase reversing are capacitive start motors and split-phase motors. Both types have a start winding and a run winding. Okay. Are they actually numbered T1, 5, 4, and 8? Is that they're there?
Very commonly, there's some variations, but that's kind of a standard.
But if they weren't this number, would it be marked somewhere? Is that on the nameplate?
Nameplate, yes.
We'll tell you what the start winding is going to be, the run winding is going to be, and what the start winding is going to be. Okay, so all right, not more to talk about that right now. Okay, let's see how this works out. Now, Steve, you seem to be familiar with this. Are they marked as a run winding and a start winding? Is that how they're shown on it?
Typically what you'll find is on the nameplate, it'll just show you the connections and say that, now this is wired for the low voltage, so it'll say for 120, connect T1 and T5 to line 1, T4 and T8 to line 2, and then it'll say to reverse, interchange leads 5 and 8. So that's how you know which one the start winding is by that nomenclature.
Okay.
It tells you which ones to reverse, which are your start leads.
Gotcha. So it'll say take T1 and T5, tie them together, put it on a wire nut, and get to line 1. Take T4, T8, tie them together, that's going to get line 2. If you do that physically, let's just say physically we do this, then this motor is going to have, let's say, a clockwise rotation, a positive rotation. Everybody with me there?
Okay.
And then here's the notes that you're saying. Forward, that's what you do. Then the instruction would say, well, if you take T5 and connect it to T4, and I'm going to look at the windings, how this connects in a while, to line 1, and T1 and T8 to line 2, 4 and 5, 4 and 5, 1 and 8, 1 and 8. That's going to be the reverse. Now, I want to go back and look at this electrically. This has line 1, so Mike, put a line 1 here and a line 2 here in the future. And then put a line 1 here and a line 2 here so I can see that that winding is connected in parallel to each other. Is that right?
Yes.
Aren't they?
Yes.
So it helps me out. So that means each winding right now would be If this is 220, then that'd be, 230. Then that's 230 and that's 230. You guys agree with me?
Right?
Yes.
Okay. Now, if this is line 1, right? And this is line 2.
They're still in parallel, just different polarity.
I got to follow this. This is line 1 that comes over here, but this is line 2. But this is line 1. Oh, no, this is line 2.
Yeah, we've swapped the run leads in this drawing, which will work equally as well. You just need to swap the relative polarity of the start with the run.
1 second. I'm confusing me here. So this would be line 2 up here, right?
Right. It was line 1 before.
And this is line 1 here now.
Yes.
And this is still line 1 and line 2.
Yeah, so
Right.
we didn't change the start, but we changed the run. So all you have to do is change their relative polarity. It really doesn't matter which one you switch.
You just change one of these.
Right,
Right.
It's going to cause the motor then to run in the reverse direction.
right. Usually on the nameplate, the ones that tell you to switch are the start windings, so you know which one it is. We've just done it the opposite way here, but that's fine. It works as well.
Oh, well, okay, well then maybe, then I guess let's just change this in the book then, right? Let's just call, you say it's usually down the start windings?
Usually it's done with the start winding on the nameplate.
All right, well then we'll
In
just,
reality, you can switch either one of them.
we'll just change these all to start then in the textbook. And DVD guys, you know why we changed them. All right? And so that'll be your start winding that we're changing. And would be with changes also to make sure that all this is identical. Okay, well, why not? Let's just make it the way it is. All right, we got that. We changed that one also. The drum switch. So the way the drum switch is working, one, it's in opposition. When I go in one direction, I'm taking line 1 to the start winding to one section, and then I'm taking line 2 to the, I'm connecting them in parallel, right? And when they're always in parallel. I'm just connecting line 1, line 2 on each of the windings. And then when I take the drum switch and I move in the other direction, I'm still maintaining line 1 and line 2 on the run winding. I'm just changing the polarity of the start winding through the drum switch.
Yes.
And then bingo goes back. And what I would be changing is, and that's where you take your drum switch. Now, would a drum switch would have a truth table on it, wouldn't it?
Right.
It would tell me that in this state right here, you have no contacts closed. But if you go in this direction here, then this is going to go to here, and this is going to go to here, and this is going to go to here, and it's going to go to there. But if you go over here, well, then those two and those two are the same, but now we reversed 2 of the leads out of the 4, and it causes it to go in reverse. I wish I had a drum switch in there, and we'll add a drum switch in the textbook. So Mike will pick that up and add a drum switch so you can kind of see how it does switch.
Now this is a single voltage motor. We might just want to make the point that if you did have a dual voltage,
Hold on. I'm glad you brought up voltages. Would this matter? Can you only reverse a single-phase motor if it's phase-to-phase? Can you do this to a
Doesn't matter.
120-volt motor?
Yes.
Washing machine motor.
Yes.
Okay.
The difference being if it's a dual voltage motor, then you've got 2 run windings in there that you're going to hook up either in series or parallel.
Hold on. Slow this down here. All right. So it's a 120 or 240-volt motor. It won't, if it was just a motor, not a dual voltage motor, then it'll work the same way as what we
Just the
talked
same.
about.
Exactly.
If I have a dual voltage motor, which would be, let's say, a 120 240, tell me what's it going to do there.
Then the most common motor, you have just one start winding and it only parallels one of the run windings. They make variations, but that's the most common. So you only want 120 volts on your start winding, but your run winding, each segment has 120. And you can put either those either in series or in parallel, depending on your supply.
Now, how would I know if I got that kind of motor? What would be the switching that would be required?
Well, the leads on it, again, would have both the high voltage and the low voltage hookups on the nameplate.
Okay.
Because you're going to have to series or parallel that.
Okay, you're
that
going to hook
start
them up.
winding, or the run winding.
You're going to hook them up so that they work on the lower voltage. But once you do that, then you need to switch the windings, one of the windings, the polarity of one of the windings.
Mike, I believe that on the single-phase motor, that's why you have T leads T1 through T8.
Yeah.
Because on a dual voltage motor,
Right.
your run will be T1, T2, T3, T4.
Exactly, which
Yeah.
you're picking up.
Right.
So you hook it
Fill it
up
in
first
there.
of all, so it runs on the low voltage, and then you start making your connections to get the reversing inside there. Excellent, excellent, excellent. I can do this. Well, we're now moving into chapter 4. Some applications, such as assembly lines, use multiple motors which must be started or stopped in a certain sequence. And this chapter is going to be talking about that. Let's go to probably unit 15, maybe it's 14, I'm not sure how the number is going to be. This unit explains how the control circuits of magnetic motor starters can be interconnected so that one must be started before the second one is energized. This type of control is often required for auxiliary equipment such as high-pressure lubricating and hydraulic pumps that must be operated before the machine itself can operate. Dan, can you give me some examples? Do you guys have processes that you have to start this and then it goes down the line?
We have many processes from conveyors to, like what you talked about, pressure lubricating systems and hydraulic pumps that can be on before machines can be operated.
And you guys have all kinds of sensors to make sure that things are in a certain condition before you even can start the first one, and you're checking it all out. That's why you're using programmable logic controllers, PLCs.
Yeah, there's a lot of times that you have a lot of complex circuits where you would have a temperature switch or a motion switch to prove that something's running, or a pressure switch or a flow switch.
So you not only want to start this one, but you want to prove that this one is actually functioning before we start adding on the next item, etc.
Yeah, for safety.
You're not dropping the box until you know the conveyor is moving.
Correct.
You want to know that it's moving, not that the contact is closed for it to move.
Yes.
And at a certain speed or whatever other characteristics. And how about Dow Chemical?
Oh, all the time. If we have a large machine that requires lubrication, for example, we'll need to make sure that the oil pumps come on first, get the oil up to pressure, and only then will we start the machine.
Okay, let's take a look at some graphics here. All right, let's see how the sequence goes here. Press the start button, energize the M coil, close the M1 contacts, interlock the M coil, close the main contacts and motor. Motor 1 has started. Once motor 1 has started, instantly at the same time, the M1 contact closed. The M1 contact in... Oh, I think this is...
That's another stop-start circuit from motor
Oh,
2.
that's a separate one. Okay. Okay, so now this contact closed, but that motor hasn't started
Correct.
because this coil had to be energized to close the contact in a separate circuit for a separate coil. That now that this is closed, I press the start button. Now I can start the next piece of equipment or energize the next M2 coil, which closes the M2 contact, which now interlocks the M2 coil. Now the second stage can continue to operate.
Right, Mike, a lot of times that M1 contact that's in the lower one, that's 4 and 5 there, many times that's called a permissive contact because it permits the M2 to energize.
I love it. Excellent, excellent. Well, let's take a look at this right here. Here's the sequence of it. Let's go. You press the start button. Oh, here. I got voltage going to one side of the coil. Done. Come over here. Goes to the stop button. I get voltage start button. I press the start button. I get voltage over to the M coil. Energize the M coil. I close. Oh yeah, close the 2 and 3 point, which continues the voltage, that's the interlocking contact. It's the auxiliary contact that's interlocking, right? It latches that coil. Then I use and you said this, Dennis, that you can add auxiliary contacts, normally open or normally close or whatever you want to. So we added a set of contacts, and then we came over from this second motor, and we go through the auxiliary contact on the first motor, that if the first motor is running and this contact is closed, then we're going to get voltage to the start-stop button of the second motor. And if, permissively, we get voltage here, press the start button, get me voltage to the M2, because M2 already has the voltage on the other side from the L2, energize the M2 coil, close the M2 auxiliary contact, which then interlocks the M2 coil. Good. I have no problem with that. Makes sense. Okay, both motors are off. That was our state. And motor 1 is running. So now we have voltage going over to the control circuit number 2. And that allows me to press the start button, which energizes motor number 2. Controls for sequencing multiple motors Here's an example where we have, well, like you said, Eric, motor 1 is a loop pump. Motor 2 is to drive it. We have a time delay relay. We have a loop pump pressure switch. And then we have a start-stop button. Oh, and then we have a motor 3. All right, let's see what the process is going to work out. What else we got here? All right. We have a ladder diagram. This is clearly showing what the ladder diagram, how it works out. We got a stop, we got a start, we got motor 1 coil, we have motor 2 coil. Which is a timing relay? A timing
Yes.
relay. You have to tell me more about that in a second. Then we have motor 3. All right. If I press the start button, we have voltage on the line 2 is taken care of. Here's a time, here's a time relay contact. Here's a lube oil pressure switch. All right, let's press the start button. I press the start button, energize this coil, close the M1 contact that interlocks the motor. So the motor's now running. I now close M1, permissive contact M1, which now permits the motor 2, which was the, the lube oil comes on. Motor. I got permissively until the lube oil pressure indicates that there's sufficient pressure. Once it gets to the point of sufficient pressure, it closes this contact.
Right.
That immediately starts the main press. Also, it starts the time delay relay, which now motor 2, okay, I got the oil going, I got the main press now running, and then there's some kind of time delay, and then as you showed us yesterday, or Steve, you did all the different time delay configurations and however you wanted to do. Then let's say 5 seconds later, this closes. Now the third motor is energized. And so that's your start, energize the coil. Here's your lube closing, energize the second one. Here's the time delay closing, energize, and Mike did a great job of having all these graphics right in order like that we can see that. Eric, you got a comment there?
Yes, this is a small solid-state timer that you can see the contacts here, and it's adjustable with these switches.
So tell me more about that. What does that mean?
Well, and so this might be where you might introduce that time delay for that time delay relay. You could either use a time delay relay like this, the white button, and adjust the time delay here, or you could use a standard relay with a solid-state timer.
And how do you adjust that solid-state timer?
There are switches here, which
Little dip switches.
the little dip
So the
switches.
instructions say that this and this and this gives you this and this time. and-
Correct.
All right. Now, is one called analog? Is the one with the one that you can turn analog? That one right there, or is not really?
Well, that's a good question. They could. This is probably analog right here because it has a potentiometer on the top. This one could also be analog, but you don't know. Could be digital. Could be
Okay,
analog.
so you can't really tell.
Can't really tell.
I just try to use that word analog whenever I can, so I can look important. Yeah. All right, here's the wiring diagram for the different motors, and I'm not going to get into that. And I'd have to sit down quietly, draw this out, put this together, do my hand-drawn graphic, kind of something like this here, and then put that together. All right, we're done with Unit 15. Moving to a master stop function. Well, this is going to be a short unit, like some of the other units are. Sometimes what you want to do is you want to make sure that a whole process stops with just one button, an emergency or a master stop button. Well, if you want everything to come off, then you want to make sure. Here's an example where you'd want to have a separate circuit for your control circuits, right? Not tap off of each motor branch circuit. You want to make sure you have 20 amp breaker at the panel, and you come over, and now you can supply all the different controls that you want to be able to turn off, and put a master stop button right there, and you just run over there with maybe a mushroom head, boom. Probably should show this with all these things energized. If all these things are energized, and maybe the next slide or two after that, this is off, you press start, you get them all energized, and all you got to do is press one stop button, which will turn them off. And then Steve has a picture. Does that say emergency
It says
system?
emergency stop on that ring. Can you see the ring around the?
Yeah, turn it down a
Hold
little
it
bit.
down a little.
Well, you know, that's the kind of stop button they put, I guess, in gas stations, right? Emergency stop button.
Fuel cutoff.
Cut it all off. Drop all the dispensers at one time. And that one might be cutting them off at the panel, might be turning off the entire panel. I'm not quite sure how that all works out. Okay, well, now we're moving into an area that we're going to call the annex. Now, this is our first book on motor control. Actually, it's our second book on motor control. Revise it. And we're making some decisions. And so we're adding a section called an annex. And what we're going to do is we're going to add a couple items here. The first thing we'll do is going to talk about a couple of diagrams, the schematics, and some wiring, just kind of something that's going to be useful. And Mike will be adding a whole bunch of other areas into the annex. Gives us some opportunity. We want to add possibly the National Electric Code Article 430 requirements to this, as well as other items. So I'm going to finish this up on some items that we know we're covering in the annex, and then there'll be some additional bonus items that'll be contained in the annex. All right, let's go on. Motor winding connections. This unit explains, or this section explains, lead designations for different types of three-phase motors. All right, we got dual voltage, 9-lead three-phase motors. Let's take a look at this one. Most common would be at 230 for low voltage and 460 for the higher of the two voltages. All right, let's see what we got here. So if we have a dual voltage motor and we're going to connect it to line 1, line 2, and line 3, which ultimately goes to T1, T2, and T3, but you have, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9 terminals. And the nameplate would indicate for line 1, connect T1 and T7. Let's see, line 1, T1 and T7, connect these two together. Line 2 is T2 and 8. That's 2 and 8. And line for low voltage, and line 3 would be 3 and 9. 3 and 9. And then it says tie 4, 5, and 6 together, so I'm going to tie 4, 5, and 6. So here's an example. 1 and 7, 2 and 8, 3 and 9, and tie 4, 5, 6 together. That would be your lower of the two voltages. High voltage connections, 1, 2, 3, and then tie 4 and 7 together, 5 and 8 together, 6 and 9 together. So T1, T2, T3. Now I know where the T comes from, why it's T1, T2, and T3. Terminals. And then you have 7 and 4, and 8 and 5, and 9 and 6 tied together, and that's how you connect to different voltages. Let's take a look how this, what does this mean? The voltage source would be 230. The nameplate would be 230, 460. But the nominal voltage is 240, 480. So don't allow that to confuse you. So we got a 240 volt source coming into a 230 volt rated motor because of voltage drop. And you have T1 and 7. Okay, 1 and 7 gets connected. As 2 and 8 get connected, and 3 and 9 get connected. That means I'm connecting these windings in parallel to each other, aren't I? So this whole assembly. So these 3 windings right here are going to get connected to 230. These 3 right here are going to end up getting connected to 230 as well. That's for the lower voltages. If I go to 480, that means that this voltage here is operating at kind of like 120, 120, 120, 120, 120, 120. And then when I go to 460, I'm going to connect this 2 windings in series to each other at 460. No, I'm sorry. This is not 120.
240 divided by
Sorry.
the square root of 3.
Yeah, okay, we can't do it that way. It can't work out because you got the configuration different. But this is going to give us 2 windings at the higher voltage, and this gives me 1 winding at the lower voltage. So the windings are both going to get the same potential. And so at the higher voltage at 460, you go T1, 2, 3, T1, T2, T3, tie 4 and 7 together, 4 and 7 get together, 5 and 8 get together, 5 and 8 get together, and 9 and 6 get together, 9 and 6 get together. And that's it. Let's go to delta. Help me out, guys. Why do I have a Y configured motor, and why do I have a delta configured motor if we still have 230, 480? Anybody know the differences and why?
It's not real important whether you have the Y or it's just the construction characteristics of the motor unless you use the Y start delta run for a reduced voltage start.
Okay, so if you're an electrician, it doesn't really matter because the nameplate on this motor is going to show you a different set of connection leads. Why it's a Y, obviously it has to do with design and there's
Yeah.
issues and there's things beyond the scope of this control class that we have to worry about, but we're trying to help somebody know how to hook up the motor. You just, in other words, you can't go to this wiring configuration and think that applies to all motors. You got to go to the nameplate and hook it up according to the nameplate and not worry about what's going on internally. And then if you go to this motor here, it's a different kind of motor, so therefore the leads will be connected differently because this low voltage is 1, 6, and 7, and 2, 4, and 8, and 3, 5, and 9, and nothing else here. But then the higher voltage is still T1, 2, 3, but then it's 4, 7, 5, 8, 6, 9. The other one was 4, 7, 5, 6, 8, 9.
The high
Oh.
voltage is the same, but the
High
low voltage is
the same,
different.
Yeah.
Yeah. So the low voltages are different. And it doesn't really matter. Eric?
Yeah, I want to bring up something real practical about a dual voltage motor. You mentioned nameplate earlier, and it'd be good to get an example because in a 230 460 volt motor, you'll see on the nameplate on voltage 230/460.
Right.
But in amperage, you'll see, for example, 4/2.
Right.
And that's real important because you pick your overloads based on nameplate amperage. And I've seen where I've watched a contractor put in an overload on a starter element, and I said, well, wait a minute, that starter, that overload looks a little bit high. So I went out to the field, read the nameplate, and he had connected the motor to 480, but was using the 240 amperage to size his overload.
Not understanding when you have a slash voltage and you have a slash amperage, that the first voltage and the first amperage are connected together,
Right.
and if we had a nameplate, and the second voltage, which would be the higher voltage,
voltage.
would it be connected to the second amperage, which would obviously be a lower amperage.
Right.
Good point. Oh, by the way, I remember hooking up a three-phase motor once with all these leads, and again, I was like, what the heck is this about? I didn't know. All you had to do was go to a book somewhere, and now today we got the internet with my little iPhone and just boom, 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 boom. I'm sure I can go to iPhone and, three-phase motor connections and pop it up, and there's the leads, and that'd have been easy. We didn't have the source then. I didn't have the education when I was first working. But I think I remember one time a motor that the leads were cut. There was nothing put on the leads. So what do you do if you get to a motor and it doesn't have any of the numbers? Do you just tell them, you better get another motor, or you better get somebody to identify? What do you do? Because how would you know if it was a Y connection or a delta connection? Any such?
An ohm meter can help you get that far to figure out if it's a Y or a delta. Because
Okay.
With the delta, you're going to have 3 sets of 3 leads. And with the Y, your continuity is going to be 1 set of 3 and then 3 sets of 2.
You're going to have
Just your
here.
continuity.
You got a set right here.
Yeah, you can
find.
figure out those sets
You
right
can
away.
find these sets, and you can find these sets, and then you'd find out, hey, these 3 are all common.
And there is a method that you can use, and I don't recall the whole method, but again, you can go on the internet and find it probably, where you can tie them together and put a...
So you can maybe tie these together, or tie it to something, and
Well,
you find out.
It's something like you tie 2 of the 3, like 7 and 8 together to one line, and then you just bump the lead 9, and then you put an ammeter on each of the other, like the 1 and 4, to find their polarities.
All right, we won't
I
go
don't-
any further
No,
other than
but there
to
is a
say
method. There is a
a method. You need to go on the internet. Somebody's already done the research that will tell
Yeah.
you step number 1, connect this, and then slowly you can make the lead
Yeah.
connections. Anything else on motors? Windings?
Well, you mentioned about not marking some of the wires. Whenever you have a motor rewound, they will probably take the dual voltage away and just bring out 1 set of leads, and they don't always mark them 1, 2, and 3.
So then you won't know rotation.
You won't know rotation, but you will know the voltage because you will have told them what voltage you've been running it on.
Gotcha.
And they do that just to save cost.
Okay, is there any reason to have a dual voltage motor? I mean, is it cheaper to buy, not a dual, or do motors just come dual voltage because it's just easier that way? Or what's the deal here?
It's cheaper for the manufacturer because they don't have to stock 2 different motors, all the iron and all the copper and everything that goes into them.
Okay.
Or if you're building a piece of equipment and you don't know what kind of distribution system it's going to go into, it gives you options.
Makes sense. Makes sense. All right. The last thing that we're going to cover, and I don't have the graphic really to do a good job on this, and I apologize. It's something that we thought about. Let's add to the book, and there'll be a little bit more graphics in the textbook with maybe a little bit more text to explain that. Is going to be a simple air conditioner, little thermostat. It's going to be single stage. It's not going to be a two-stage. Here's your compressor, and there's going to be a set of relays in here. Oh, no, there's going to be a relay that's going to be operated by a 24-volt control, and I guess that'd be AC control. And then we have a thermostat. Then the air handler, in this example here, that this would be, let's say, a heat pump only, without any supplemental heating. This is just good on or it's off, so there's just one relay with a set of contacts. And then we have the heating element, which would also have a relay that will turn on the heating element. So that's one relay with 2 wires. This is the compressor with 2 wires. Then I have the blower. That'd be another relay. That's 2 wires. Then we'd show the transformer. Well, that's going to be primary 2 wires, secondary 2 wires. So I have 2 wires off the transformer, 2 wires from the heating relay, 2 wires from the fan relay, and 2 wires from the compressor relay. And somehow I got to get 2, 4, 6, 8. I think there's 8 wires. Somehow I got to get them together to the thermostat. So let's just take our time. Well, the practice, well, no, not the practice. I guess the standard is your thermostat is going to have a yellow terminal, and that'll be identified for the yellow wire. That's usually what W means. I mean, the Y. The thermostat will have a W terminal. That would be for the white wire. It will have a G terminal for the green wire if you use color coding. I mean, if you actually use these colors. And it will have a R terminal for the red wire. And it will not have a terminal B at all for the common. It's just going to have yellow, white, green, and red. And this is a single-stage, simple thermostat, not two-stage. The practice is, let's just assume that we're running a raceway for convenient purposes, and we're pulling our conductors, and we are going to color code the conductors. Are you with me? So we have control of color. If that's the case, yellow is for cool. That's the compressor. I would run a yellow wire over to one side of the relay, and the other side of the relay, I will then take a common conductor, and I'm going to use the color blue. So the common conductor comes back. If this was the wiring configuration, the blue wire comes over to the thermostat, and since that's common to the transformer, the blue wire will travel over through this cable and go back over to the blue terminal that's going to go to the common of the transformer. If I can take 24 volts to the relay of the compressor, it closes those contacts, compressor kicks on. Let's talk about the fan. The fan has a common that also goes over to the transformer. And the fan is going to be controlled by the thermostat, and the fan is the green colored conductor. So I'm going to take a green wire from the thermostat to the fan relay. I'm taking a yellow wire from the thermostat to the compressor relay. Then I have the heater, and heat is the white terminal or the white wire. Then from the thermostat, I'm going to take a white wire to the heating relay, and the heating relay has a blue wire going over to the common of the transformer. So what do we have? Oh, then I have a yellow for cool. I have green at the thermostat for fan. I have white at the thermostat for heat. I have the common conductors not making a termination at the thermostat, but all common conductors go over to the transformer, common terminal. Then I need to have power to the thermostat. I leave the transformer secondary, and I run a red wire to supply the thermostat. If you take the red wire, and you take the red wire, which is your power, and you touch the green wire, the blower should blow. You'll hear it turn on. If you take the red wire and you touch the compressor, of course, assuming power's on there, you'll hear the compressor kick in. You take the red wire and you touch the white terminal of the thermostat, then you're going to be smelling the heater elements heating up without the ability to cool them down because we're not moving any fan. So the way a thermostat works out is that when it goes to heat, it closes two sets of contacts. It closes the contacts for the W, for the heat, but it simultaneously closes the green contact in the thermostat so that the fan is going and the heating is going at the same time. When we go to the compressor mode, where the thermostat says cool, gets voltage to the relay for the compressor. At the same time, it energizes the green wire, closing the fan so that the fan works at the same time the compressor works. So the fan goes with the compressor, fan goes with the heat, so it's going to run in both times. And that's the simple basics of a basic thermostat. But we're going to add two-stage and maybe some other thermostats to the textbook. Any comments at all on this, guys? Steve?
Yeah, like you say, that's the simple of it. There's also some things in there they might need to be aware of, like time delay relays and various things that stage things off and on so that the fan will come on before the heating elements or before the gas pilot or the gas. So there's some timing that takes place in there too, but it doesn't affect the thermostat.
All that timing is all done by the equipment.
Yeah, in the unit.
So now I know I have a thermostat. It has multiple stages, and it has supplementary heat, and it has a heat pump, and it has resistant heating. And when I looked at my wires, I'm like, I have no clue.
Yeah.
And guess what? You don't have, I think it's like there's like a W1 and a W2, and then there's a yellow, a Y1, in other words, in that particular application, you know, if you get more than this basic thermostat, you need to get the thermostat, you need to understand the wiring diagram as, okay, what wires am I supposed to bring, because you now have multiple staging, you have supplementary heat that kicks in when it gets below a certain temperature that the heat pump is no longer being efficient. Then all of a sudden it goes on to resistant heating. There might be supplementary heating in the heat pump itself, and then you have additional heating in the actual air handler. So it can get pretty complicated. What I didn't know, I told you this story, my first experience. When we started this thing, I got fired because I couldn't hook up this thermostat. I didn't know and we didn't have the technology then we have today. All I needed was the instructions. Yeah. I didn't have to know off the top of my head how to hook this up. I needed to have the instructions to that equipment for that thermostat. What are we trying to achieve? If I had the knowledge of that, but like you said, Steve, if you just go somewhere and there's no thermostat there, and you got a bunch of wires sticking out for a thermostat, and you don't know that there's controls and delays and how this all work out, you can't just be taking a thermostat now trying to make the things work. You're going to have to get with the manufacturer. You're going to have to understand the process and what needs to be achieved, and make sure that you have the right thermostat, and then go through it, and you're going to be fine. So hopefully, don't feel like you're supposed to know this. You're supposed to know that you need to get the information, get a quiet spot, sit down and look at that without people breathing on your neck, like, well, you're going to get that done? What's going on here? I thought you had it done by now. You know, that whole thing works out.
And then it's all series or parallel relationships.
Yep. I tell you what, yes.
Well, also with thermostat, I can't emphasize enough, keep the instructions and look through the instructions, because there are other things on thermostats. For example, sometimes you open up, there's jumpers on a control board. And if you cut the jumpers, then you cut them to provide different options, like a regulation band, and this, or if it's Celsius or Fahrenheit, for example. And so really look at those instructions.
Okay, well, it's about the best we could do right now. And I'm sure that we can do a better job in the future, and we'll continue to improve. I hope we're able to achieve what our goals were, and that was to take you from knowing nothing about controls, giving you the foundation of some basics, the terms, and how these things can be approached, and how you can solve some of the problems, and give you the confidence to know that you don't have to know everything. But also, as you gain knowledge, you become the go-to person, and Steve keeps saying that, and that's when you become more valuable for yourself, for your family, for the industry, for the employer, if you're not the employer itself. So we're always striving to be better and better and better. Please visit our website. Our website is MikeHolt.com. And, you know, there's so much free tools. There's newsletters that go out there. If you have a question, like, how does this work? I mean, you had a control question, you can just go to our MikeHolt.com, go to the forum link and post a question. And trust me, you know, you're going to get your answer. How many of you guys here on the forum get my newsletter? So all you guys get the
All of
newsletter.
us.
Okay. And so the key is those people that really want to stay connected. I send out a newsletter 3 or 4 times a week about a lot of different things. And you can decide whether you want to read it or not. If it's not important to you, you delete it, and you can choose the topics you want to receive. You have questions you can post in there. There's free software. Please, please, please go to MikeHolt.com. Take a look at all the free links and all the free information. Then if you find out that you need a product, you want to educate yourself, you want to go to the next level, you know, we'd love to be able to help you. You know, there's something you can order online, or you can contact our office. Let's get a closing with these guys here. Let's see what these guys have to say that maybe they can kind of leave you something, rah, and then I'll leave you with something. Steve, we'll start with you as we always do. One second. You know what? Before we do that, I want to take a time and just, you know, thank these guys. I mean, you know, I'm just a facilitator in this particular course, but even if I was the expert, these guys are experts on top of what we do. And as a team, we work really, really carefully. We work together to give you some insight, little tiny things of information. I mean, I've been in the trade now since 1970, so that's what, 38 years. Steve, how long have you been in the trade?
74. So
74,
34 year.
34 years. Eric?
I guess about 32.
32? Dan, you're probably a young pup here. How long have you been?
Well, I started out as a millwright, but I've
No,
been
we don't
like
count that.
Christian since in '88.
Okay, 88 now, so 20 years?
20 years.
29.
29 years? So you got, and Mike Coberth, how many years?
74?
74, so you're about 34 years like Steve?
Yep.
You know?
About the same
So
as I do.
we're talking 100-something years of experience in all different aspects coming together, bringing the combined knowledge to give you the tools you need. And so I want to thank these guys because they've done a great job. And I tell you what, I feel a lot more confident in controls. So I think that's great. Hey, Steve, tell these guys something.
Well, I just like to encourage the guys, you know, that even if you just got a couple years experience or just a beginner, you know, to feed your thirst for knowledge. You know, the more that you learn, the more that you know, the more you're going to be the go-to guy, and the more satisfied you're going to be with your work. If you can understand what you're doing, it makes it much more enjoyable. And Mike has got just a wealth of products for the electrician, not only on controls, but on electrical code and theory and all those things. So anytime you can learn, it's going to help you to better yourself.
All right. And Eric, my engineer.
I'm going to go back to the statement that I thought of several years ago. It's the power of knowledge versus the pain of learning. And all learning is painful and uncomfortable. But if you can submit yourself to it and commit yourself to it, the knowledge that you get from that gives you power to do things and to make your life easier. Ultimately, all of this stuff makes your life easier.
Dan, this is a new experience for you because these guys have been doing this for you know almost 6-8 years for me in this video team, and this is your first time that you've had opportunity. And I want to thank you personally because I think you've done a great job, and we're really, really pleased that you're here. And so next time we do the motor control course and maybe other courses, we'll make sure you'll be part of the team. So anything you can convey to the student watching this?
Well, thank you, Mike. I appreciate that. You know, I'll go back to saying that the basic 3-wire start-stop circuit is the most important circuit you'll learn. I'm glad that we've held Mike to appreciate him as much as he does now.
That's true. I love 3-wire circuits.
But that's the basic building block that you'll build on, and it's used over and over when you get into the more, you know, complicated circuits, and you get into the PLCs, you get into if-then else statements, you get into wonderware, or, you know, operator interface controls. The start-stop is a basic building block of everything that you'll build from.
Well, thank you. Appreciate that. That's great. Dennis?
Just go back through the videos, go back through the book, pick up equipment like this, and take a meter and just sit there and take some time and troubleshoot it and get a good feel of it. And you got to stick with it. You got to review it, and you'll get a better handle on it. It'll come.
All right. Well, I'll give just a final little thing. I appreciate it. appreciate you taking the time, really to watch this DVD. And if you get a chance to completely read that book and answer those questions, Mike Horwath, he's working as a team here. We're doing a good job. And Mike, you did a great job. Everybody loves your graphics and appreciate everything you do for the industry. And God bless. Talk to you guys later. Bye-bye. Let's take a look at Article 430, motors, motor circuits, and controllers. All right, let's go to Section 430.1, the scope of Article 430. Article 430 covers motors, motor branch circuits, feeders, the protection, overload, control circuits, controllers, motor control centers. This is a big deal. And in my textbook, there's 2 ways that I think you can become an expert in motors. Number 1 is take a look at Article 430, get your code book out, highlight it, tab it, and mark it. And of course, we're going to cover a little bit of information today. Also, we have a separate course on electrical calculations, and there's a specific DVD on motor calculations that we get a little bit more in detail inside as far as calculations. All right, let's go on. 430.6, the full load current versus the motor nameplate current rating. Full load current. When the code uses the term full load current, it's referring to the actual National Electric Code values. And that's the values that's listed in tables 430.248 for single phase and tables 430.250 for 3-phase. So I really suggest that you take the time, you stop it, you look at table 430, 248, because they moved it around, and table 430, 250, single phase and 3-phase. Now, Ryan, there's a lot of tables in there. And so what I did, matter of fact, let's take a look what I did back 30 years ago when I was in 430. I have a tab on 430. 440. Here's my tab on motors. I'll put this up here, Scotty, so you can see it. Start in the beginning here. I marked DC, so I wouldn't screw up. Over here, I marked it single phase. I even put formulas on how to calculate the VA of a motor. I circled the heading. It said full load current. I wrote FLC. I even made a cross-reference. Look back here in the code book here. On the top here in the code book, I made a cross-reference between this handbook and the National Electric Code. So if I wanted to go to the code book and not have a handbook, I'd be able to make a cross-reference. That's the kind of detail I had. Let's go to the next page here. Then I had 3-phase. I identified 3-phase. I made the note FLC. I circled the word induction type because it's easy to go into a table and not realize there's multiple things in there. And synchronous type. I made how to calculate the VA of a motor. So when I wanted to do calculations later on, I didn't have to figure out what was going on. And when I went to my code book, let's take a look at 430. Let's see if I did 430.6. What did I do on 430.6? Quickly turn there. 430.6. Nope, I didn't cover it at that time. But you can see my notes in here. I even put little pieces of paper, had something in there, highlighted things I thought were important in pink, circled words, made references to other code rules. In red, I even identified what step number, if I was doing a calculation, that would be step number 3. Okay? This is what you have to do. Nobody told me to do this. I mean, I'm not a smart guy, so I don't remember things very well. So by me putting things down, and when I get to it again, I'm like, oh yeah, I remember how that works out. So the code book gives us the full load currents. So you have the code book currents, and what you also have, is what the motor nameplate rating. Let's take a look at the graphic again. So you have the motor nameplate, and then you have the code book full load currents. You use the table of the code to size the conductors, the disconnects, the short circuit and ground fault protection devices, and then you use the nameplates to size the overload protection. And right now you're like, I don't know what you're talking about. Okay, if nothing else, you should know this. There are full load currents listed in the code book, and there are nameplate values that's listed on the nameplate. And we got to be careful in which one you use. Just like you don't use a three-phase table for a single-phase motor full load current, just like you don't use synchronous motors for induction motors. In other words, you got to be careful in what you're doing. So do what you need to do to get rid of tables, cross them all out. You don't have to do what I did, but at least you can get rid of things that definitely don't apply, or circle things and highlight things that you do apply. I really believe electrician in the field should have the ability to size the wire to a motor. I really don't think we're asking too much. You should be able to go out there and say, hey, I got a 5 horsepower motor, 208 volt, 3-phase, boom, let's go out there, size the wire, size the protection. You know how to size the raceways and the conductor size. Why not? I mean, aren't you like an electrician? You know, aren't you an engineer? Shouldn't you be able to do this kind of stuff? All right, let's take a look at the rule. Motor full load current rating. Now, full load current rating is FLA. That's not full load current. Ryan?
Well, I was just going to mention while you're on that previous graphic, especially if you're new to motors, that's something you need to burn right into your frontal lobe, is what is FLA, what is FLC, and what do you use them for? You'll never get any question right on a test if you don't understand this.
FLC, right? It's a code book.
Right.
FLA is the nameplate.
Yes.
Full load amps versus full load current. Full load amps, well, there'd be no reason for you to calculate this unless you had an exam question saying, hey, I have a 1.5 horsepower motor, and it's 3-phase, and it gives you the efficiency and the power factor. Well, then you take the formula, 746 times horsepower divided by volts divided by the square root of 3 divided by efficiency divided by power factor. And of course, there was no reason for any electrician to have to do this. Okay, there's no reason. Click on a nameplate. But a manufacturer had to calculate out the full load amp somehow. They need to know what horsepower is it, what's the voltage, what's the efficiency, what's the power factor, single phase, 3-phase, and they kind of go through the calculations, and that's how the nameplate is calculated. But guess what? We don't care. We don't use nameplate. So who cares? We're never going to use a nameplate. Let's go to 430.22, conductor sizing. Conductors for a single motor are sized no less than 125% of the table full load current, not the motor nameplate current rating. We get the table full load current, 247 for DC. I don't think we see a lot of DC motors. Maybe there's a space there in that comma. 430.248 for single phase, 432.50 for 3-phase. You use the code book, not the nameplate, to size the conductor. So let's get an example here. If the motor is 7.5 horsepower, and this is going to be 3-phase, then 3-phase, I would go to table 430.250, and that says that the full load current is 22 in the code book. Well, I sized the conductor no less than 125% of that. 22 times 1.25 is 27.5 amperes. And then if I remember right, it was 110.14 C1. Ryan, double check me. I don't know if it's C1B that says that motors for under 100 amperes, is it C1B?
C1A4.
Oh, C, oh yeah, A, like I say, C1, because it's 60 degrees C is A. C1A4 in motors, that motors are sized to 75 degrees C. So if the motors are 75 degrees C equipment, and the breaker is 75 degrees C, well then I would just go to table 310, 15B16, go to the 75 degrees C column, when I'm talking about all this, put me on pause, get to your code book. This is not something, when we get into calculations, this is not something you should be sitting there. And actually, I don't have a problem with that. I don't have a problem you watching me go through just to kind of see what I'm doing, put it on pause, go back and watch it again, and then pause me as you go along as I step you through each of the functions. Go to this code book, to this number, go, and I give you these references. I mean, I'm throwing out these references not because I'm trying to impress you. I'm throwing out these references because I want you to say, oh, let me go check that. You should be looking at, every time I give you a code reference in this DVD, if it were Mike Holt, which I never had anything like this here, and this is why I produced what I produced, because I was so frustrated. If it were Mike Holt and I had this DVD, I'm going to tell you one thing. Every single time that guy used a code reference, every time, if he said 110.14C, and guess what I would have done? I would have found the guy made so many mistakes when he made references to the code because he said 110.14C1C, or but it really was C1A4. So you would have, I would have caught those little tiny things because the guy's trying to say it real quick and he makes slightly off and maybe even use the wrong article. Well, if you take a look at this and you knew he meant to say this. So I'm catching all these little things and I'm going to the code book back and forth, and guess what you're going to find out? Wow, how often do you use this rule? How often do you use that rule? How often does this come up? How many times you're going to be able to become an expert in the material. So don't just listen and move on. Listen, go back to the DVD, back and forth, back and forth. So back to our calculations. 22 times 1.25, 27.5. I go to table 31015B16. I go to 75 degrees C. I look it up. I need a wire rated 27.5 amps, and I guess it's 10 gauge. It's just that simple. Even though I say it's just that simple, it's the simple things that really catch you. It's like, Mike, where in the code does it say this rule? And I'm like, gosh, it's such a simple rule that everybody knows it that we never look it up. Those are the hard ones. Those are the easy ones to trip up. Watch this. We size the conductor to the FLC, okay, which is in the code book. Let me tell you what you don't do. If you're physically on a job site and the motor is there, you do not ever look at the nameplate as it relates to conductor sizing. You don't look at the nameplate because that's not what the purpose of the nameplate. And let me tell you why we don't look at the nameplate. Because the code book gives you a value of currents. The motor that you put in specifically might not be the motor that you're going to replace someday, because we don't know the efficiency and the power factor of every motor every single time. So when the code says, take a look at the graphic here, this motor draws 22 amps full, this motor has an FLC of 22 amps, I'm sure that most 7.5 horsepower motors, 230 volts, three-phase, are not 22 amps. But there probably is a motor, depending upon the NEMA configurations, that it could go up to a maximum of 22. So we want to make sure we have a conductor there that will always be available for a 7.5 horsepower motor, not for the motor that you specifically put in. So we do not size conductors based upon the nameplate. We have to make sure we use the full load current. Let's go on now, sizing conductors if you have several motors. Conductors must be sized not less than 125% of the largest FLC plus the sum of the FLCs of the other motors. So if I have two 7.5 horsepower motors, I do not look at the nameplate. I look at the code book. We already determined it was 22. So 22 times 1.25 plus 22 amps comes out to be 49.5. We're going to go through that mental routine that we're going to use 75 degrees C terminals because the breakers are rated 75 degrees C. Going to table 31015B16, I need a wire rated 49.5 amps. 8 gauge wire is rated 50 amperes at 75 degrees C. Pretty straightforward, not complicated. Don't go to the nameplate rating. All right, let's move on now to the protection of a branch circuit. 43051, branch circuit protection, the general requirements. A branch circuit, short circuit, and ground fault overcurrent device protects the motor, the motor control apparatuses, the conductors against short circuits or ground faults, but not against overload. We talked about this when we were in Article 240. We talked about the definition of overcurrent. We talked what an overload was, what a short circuit was, what a ground fault was. And generally, when you provide overcurrent protection, overcurrent, then the definition of overcurrent, Article 100, has to do with overloads and short circuits and ground fault. Generally, when you provide overcurrent protection, you put in one device. It's a fuse or it's a circuit breaker, and it protects against overcurrent, short circuit, ground fault, and overload. When you get to motors, we have different characteristics. This is not a light bulb. This is not a computer. This is a load that when you first turn on, it has a unique set of properties, and then it ends up changing once it gets to a certain point. So you have to be able to consider the different. This thing is moving around. It starts here and it goes there. So we got to be able to size it for here and then there at the same time. So we're going to take a look at the rules here. We need to provide overcurrent protection. Watch this. This is an overload. That's going to protect the motor against excessive current. And then over here, we're going to have a fuse breaker, and this breaker is going to protect this motor against short circuit. Right now, this motor has a full load current rating, full load, that's a nameplate. It has a nameplate rating, we probably should indicate, of 16 amps, the nameplate. But if it was drawing 24 amps, well, then we have a problem because it's overloaded. So what's going to happen? These overload devices okay? They are designed for slow current rise, probably slow temperature rise, probably more than slow current rise. It's a slow, it would be a slow temperature rise, and it's a current that's going to be long duration, and the device responds slowly. So if I put 24 amps on a 16 amp overload, this baby is not like instantaneously opening. What it does is it works off of heat. So if you put 24 amps on a 16 amp intended load and you provide an overload device that's looking to protect that motor of 16 amps full load amps, well, if you put 24 amps on there for just a second or two or a minute or two and it comes off, it's like, oh, okay, we're not worried about it. But if it's going to be on there for an extended period of time, now the overload device is going to be thermal. It's going to sense it. Of course, it can be done electronically as well. And then once it gets past the point of realize, okay, wait a minute, now this overload, this current has been lasting too long. And we're not talking about seconds. We're probably talking maybe in minutes, depending upon what the overload is going to be. So it's slow responding. Now let's talk about short circuit protection. What happens if there's a ground fault or a short circuit and it draws 1200 amperes? Well, these overload devices are not going to respond because they take a long time to pick up heat. However, the short circuit protection device up here is intended to pick up a short circuit. So your short circuit and ground fault protection devices are designed to protect against short circuits. The overloads are designed to protect under an overload condition. And when you have the short circuit ground fault protection and the overload, then that provides over current protection. Short circuit and ground fault devices, I'm making a statement now, are sized between 150 and 300% in accordance with 430.52 table. Short circuit and ground protection is designed for fast current rise, short duration, and a fast response time. Let's go a little further. We can see what we're talking about. Here we go. You have a motor that's starting, and it starts at lock rotor current. You see, you take a winding of a motor, and you wrap it inside the motor, and then you turn it on. Well, the instant you turn it on, it's a dead short. But as it starts carrying current, alternating current, it has an expanding collapsing magnetic field. And we covered this in the electrical theory class. Very, very important that you get my electrical theory course and you go through that whole thing because it's practical electrical theory. I'm just going to hit a couple points here and not explain how this works out. You have a coil, you have counter EMF, you have magnetic fields inducing a voltage that's going to be at 180 degrees out of phase of the applied voltage. And what this is called, this is Lenz's law. This is where Lenz's law, it starts short circuit, the inductive reactance gets involved, and all of a sudden now it changes the impedance of the circuit. You should be understanding everything I'm talking about. If not, you need the electrical theory library and go through that. It changes the impedance of the circuit from this low impedance, because we had only resistance, you're now adding reactance, and the reactance and the resistance combine together, which increases the impedance, and it changes the current from starting current to running current. Simple version here. Generally, motor starts at lock rotor current. Lock rotor current is approximately how many times running current? Some of you guys maybe already know this. The answer is 6. It all depends on the design of the motor. Very, very high efficiency motors will have a very high inrush current. Now, I'm going to get a little bit off schedule here, or just a little bit off topic. High efficiency air conditioners, scroll cage air conditioners, high efficiency. One of the disadvantages to them is that when they start at short circuit, and the reactance is so low that that short circuit current stays high for enough time that all of a sudden the lights in the house, they just do a little tiny dim, and then they rise back up again. We're only talking about a couple cycles, but the eyes will notice a slight, like 1% change in illumination is going to be the square of that. When I say 2%, it's going to be 4% change, and the eyes can sense that. So air conditioning loads that are high efficiency have low inductive reactance, because that's how you get efficiency out of that, and it causes the current to be high. So fault current would be much higher if you had a fault condition. Back over here in motors. Motor starts at lock rotor current. The higher the efficiency, the higher the lock rotor current. So it starts lock rotor current, and then it starts going down, and then we have what? We start in picking up reactance. We start getting, the impedance goes up, and then all of a sudden now we're running at this. Let's say this motor is drawing 22 amps. Well, that's what it's drawing. But it might have started at what? 22 times 6? I don't know what that comes out to be, 132 or something like that. So guess what? During the starting current, I need to provide some protection. Well, I can't provide overload protection because this is too fast. So I have to provide short circuit protection that if during this period of time there was a short circuit, let's say the short circuit was 10 times. See, short circuits are considered to be about 10 times the rating of the protection device. So 10 times. So if you had 22 amps, it's going to be about like around 200 amperes, something like that. Well, if you put 200 amperes on a breaker, well, it didn't expect to be that high, so therefore it's going to react in that particular case. So it starts at 6 times. Let's size the protection device, allow that motor to start at lock rotor current. So there's a formula in the code, and the code says, well, use this percentages. And it also says, well, if you use this percentage and you put that breaker in there and it doesn't hold, like, okay, put a bigger breaker. It doesn't hold. Okay, put it. In other words, you got to put a breaker to allow it to start. But here's the disadvantage. The larger the rating of the breaker that you go to start, then you obviously have no overload protection. You can't protect that motor that draws, let's say, 22 amperes if you're going to be starting it at a protection device at a certain percentage significantly above the rating of that motor. So look at the rule here. Short circuit protection is going to be sized between 150 and 300%, right here. Overload protection is between 115 and 125%. So you can see we can protect the motor when it runs, but we need to start the motor and get the short circuit protection. 43052, branch circuit, short circuit, and ground fault protection. All motors, a motor branch circuit, short circuit, and ground fault protection device. Now, they didn't say motor overcurrent device. They said motor branch circuit, short circuit, and ground fault protection device must be capable of carrying the starting current of the motor. That's what the code says. It has to be able to allow it to start. And then there's a table. And basically, the table says, depending upon the type of the motor, depending upon the type of the protection device, you have a different percentage. If you're going to be using other motors, not wound rotor, let's say not DC, let's just say we go to other motors. If you're going to use a one-time fuse, then the fuse would be 300%. If it's a dual element fuse, then you go 175. And if it's an inverse time breaker, then you're going to go 250%. For the convenience of this presentation, let's just assume that we're going to be using circuit breakers. And if I'm using circuit breakers, I'm going to use 250. If I'm using fuses, then it'll be identified in the example that we have, if we have any fuses. So let's go into the example now. Let's take a motor, 2 horsepower. It has an FLA, full load amps, which is the nameplate of 11 amps. But it has the code book, so we need to say in there nameplate, and then 12 amperes, which is the NEC. Well, we size the conductor based upon the FLC, which is the listed in the code book. 12 times 1.25 is 15 amperes. No problem there. 15 amps, you go to 310-15B16. We're going to go to 75 degrees C because it's motors, assuming everything is rated 75 degrees C. 14 gauge wire, rated 20 amperes, and that's how I'd size the conductor. Not anything more complicated than that. Take 125% of the full load current, size your conductor. Now look what happens here though. See, we're in 43052, C1. We're talking about protection, but we're talking about short circuit and ground fault protection. We're not talking about overcurrent protection. That table tells us that inverse time breakers that go 250%. 12 times 2.5 comes out to be an even 30 amperes. You go to 240.6, standard size breakers. It's a 30 ampere breaker. So you put 30 ampere breaker on 14 gauge wire. And the purpose of this breaker is to protect the 14 gauge wire, to protect the controller, to protect the motor circuit conductors and the motor under the condition of short circuit and ground fault. It's not to protect the motor and the conductors and the components against overload. Overload would require you to have an overload protection device. Now, some people struggle with this, with the fact that, wait a minute, you're telling me I can put a 30 amp breaker on a 14 amp wire? Well, I'm telling you, you size the wire to the code, and the code says you take the full load current at 125%, then you go to table 310-15B16, and you go to 75 degrees C column, and you size the wire, and you're done. Has nothing to do with the protection. And I'm saying, how do you size the protection? Well, you go to 430.52, C1. You go to the table. It says inverse time breakers, 250%. You go to the full load current listed in the code book. You get the full load current times 2.5. You look up that device. You go to 240.6. If it doesn't correspond to the standard size on the protection device, you go up to the standard size protection device, and we're done. But Mike, a 30 amp breaker, 14, listen. If you take 14 gauge wire and you put it on a 30 amp breaker and you have a short circuit or you have a ground fault, that current is going to draw more than 30 amps under short circuit in ground fault condition. Not overload. We're not trying to protect against overload. That's why it's called the short circuit ground fault protection device. It will protect the wire against short circuit and ground fault. Now, you might not like this. Oh, I don't like this. Okay, fine. I don't care. But if you're going to take a test, how about if you know how to do it right? You know, you make sure that you know how to answer the question and get the correct answer on that. And that's how it works. Let's go on to the next graphic. Okay, let's take a look at an example about 43052 C1 exception. We have a 7.5 horsepower motor, 230 volts, three phase. We go to 430 250. We find out the motor draws 22 amperes. Okay, we size the conductor at 125%. So we're going to take, okay, we don't have an example there, but let me just do the number. Oh, we did it previously. That was 22 times 1.25 came out, I'm going to, whatever the number is. It was a 10 gauge wire, but we're talking about the exception here.
27.
The protection. You size the protection in 43052C table. The general gives us 250%. 22 times 250 comes out to be 55 amperes. 240.6 does not list a 55 ampere protection. This exception says that when you do the calculation on the branch circuit, if it doesn't correspond, go up to the next standard size. So we'd have a 60 amp breaker with 10 gauge wire. Again, this is short circuit and ground fault protection, not overload protection. Let's just do a little summary here. 43052, and the table 43052 tells us that we size the short circuit protection at between 150 and 300%, depending upon the motor type. You size the conductors to the motor on 43022A. You size the conductors at 125%. And the overloads are sized between 115 and 125%. So if you have your short circuit protection and your overload protection, that will provide the overcurrent protection required for the circuit. Now watch this. More than likely your breakers are going to be 250%, your conductors 125, so you can expect that your protection is going to be greater than the conductor by a considerable amount. This is a different example. 28 amp full load current for a 5 horsepower 230 volt motor. We ignore the full load current for the purposes of sizing the conductor. We take the conductor, 28 amp full load current at 125%, comes out to be 35 amperes. We go to 75 degree C column, table 31015B16. I guess that comes out to be a 10 gauge wire. We don't need to have the insulation on here, 10 American wire gauge. And so we use the full load current to size that. You size the protection at 250% of the full load current, which was identified on the table. We do not use the nameplate. 28 times 2.5. This comes out to be exactly 70 amperes. And therefore, we're going to size this protection at 70 amperes. So we use the full load current for sizing of the conductor and the protection, and we use the motor full load amps for sizing of the overloads.
So kind of a interesting point. We didn't cover overloads. How
Okay.
you size them? You know, how do you?
There's a reason why I did not put any slides on sizing of the overloads, because we don't do calculations in sizing overloads. If you're taking a test, you do. The way you size overloads is you get the overload protection device, and you look at your motor nameplate rating, you take the cover, you look at it inside there, and it gives you current ratings. And it says, okay, what is your current rating? And when you figure out what your current rating is, in this case here, the current rating is 26. You look at 26, you take the cover. We don't do calculations. And then you find the cover, and then you have dip switches, and you change your dip switch settings, or you go out and you buy an overload device, a mechanical device that you're going to put, an electromechanical device, and you put it in there. The code does provide all kinds of percentages inside here. If you were actually going to do the calculation and you were actually going to put an overload device, that would only happen if you were going to be putting in a fuse. Other than that, the overload device is part of the controller, and that's the reason why I didn't get into the calculation. If I'm in an exam prep class, well, yeah, you're going to take a test. They're going to ask you a question. Hey, I got a motor with a service factor. I got this temperature rise. I got the nameplate rating. I get the FLC. What would be the overload device size? Then we're going to get into all the calculations. Do you follow what I'm saying, Ryan? And that's the reason why I didn't want to cover it here, because it doesn't belong in understanding the AC. If I have to compromise time, that is more of an exam preparation and why and how you do that. And I'll tell you a short little thing about that. It is important to understand overload protection. Short version story, I was living in Fort Lauderdale. I had a boat lift, and every once in a while, I noticed that when I was barefoot water skiing, I come back, my boat lift was up. But when I got back, my boat motor lift was up while I was skiing. I didn't understand what happened, and my motor burnt out. So I go out and I buy a $400 replacement motor, stick it back in there again. 6 months, a year or two later, my lift is up. And I'm not a smart guy, but I'm starting to pick up a trend here that when my lift is up, my motor's burnt out. Guess what? My motor's burnt out a second time. All of a sudden, everything is fine. I can't figure out what it is. About a year or two later, I come back and I see my lift up. That means it's the third motor that burnt out. What I found out was this, and I happened to see this. There was a bird that landed on the handle of the lift. See, this takes the lift down, this takes the lift up. A bird came over to the handle. When he landed on the handle went down. So when he went down, he did what? He pushed off to fly away, and the handle went into position that lifted the motor all the way up. I had no overload protection on this half horsepower motor because it ran back over to the source. Now, what I did was I added a fusible disconnect. I look at the motor nameplate. It drew 6 amps. I sized an overload device. I couldn't find one at 115, 125%. I didn't know what to do. So I went ahead and I bought a 6 amp fuse, put it in a fusible disconnect, and I never lost the motor again. So if you're really trying to protect the motor against overload, you need to have overload protection. Now, many times overload protection is internally part of the motor, but many times you can get small motors that do not have internal overload protection. And if you want to protect the motor against overload, you need to understand 430.31 and 32 in sizing overload devices. So that's why I didn't want to get too detailed, other than I want to give you a conception of overloads, but not all the calculations involved. Eric, do you want to make a comment before we're done here in 430?
Yeah, everything you're saying in overloads is correct. There is one caveat. When you're dealing with electronic overloads that have potentiometers, and these things have scales on them, and some of the manufacturers, specifically ABB and Cutler Hammer, will say, look at the nameplate, and if it says 12, just dial the potentiometer to 12. But if you have a Siemens overloads trip at the setting. So you do actually have to make the calculations on those.
All right, excellent. So make sure you look at our book. We have examples, and if you really want to know more about that, we'll get into the calculations portion that we'll be recording in another course. Let's go on to 430.62, feeder protection. Boy, this is a rule that I think nobody ever gets. I mean, I teach this for years. Feeder conductor overcurrent device size, not, you know what I'm going to do? I'm going to underline this thing while we're all looking together here. Maybe that'll help you. Size, not greater than, okay? Not greater than. So whatever this answer is, it's not going to be greater than whatever our answer is going to be. Then the largest rating of the branch circuit, short circuit, and ground fault protection device, so the largest protection device of the motors, plus the sum of the full occurrence of the other motors in the group. Let's go with an example here. So this device cannot be greater than whatever the calculation is going to be. And unfortunately, the calculation is perfect here. So we know we have a 5 horsepower motor, and it's a 70 amp breaker. And the reason we have a 70 amp breaker, I don't know if we did a calculation previously in the book. 70 came out to be 28. Get your calculators out, guys, if you would, for me. What's 28 times 2.5? Does that come out exactly 7? I think it comes out exactly 70 amps.
70, exactly.
That's what we
Spot
did.
on.
All right, so that's a 70 amp branch circuit, short circuit protection. How about a 3 horsepower motor that draws 17 amps? So 17 times 2.5 is,
42.5.
what is it?
42.5.
40, and it doesn't correspond to standard size, right?
Right.
So therefore, branch circuits can go up to the next standard size. I got a 45 amp branch circuit protection. I have a 70 amp feeder protection. The feeder protection device is sized no less than the largest branch circuit protection, 70 amps. You can see how Mike highlighted this in red, plus the full load current of the other motor. Not greater. We have it in there. Where's it? We have the word in here, not greater than anywhere? Yeah, I don't know where it's. Okay. Okay. So it's not greater than 70 plus 17, then it would be the next size down. So not greater than 70 plus 17, not greater than 87. Well, you can't put a 90 because obviously that's greater than 87, so you have no choice but to put an 80 amp device here. Okay? And that's how now, just so you have an idea, what is, I'm not even going to go any further. Let me just stop it right now. This is not a calculations class. I could go on and get a lot more deep, though. So I'm going to stop there. By the way, the circuit conductors on this was sized at 28 times 1.25 plus a 17, so 25, that's 35, that's 45, that's 52, I think. So I needed 52 amp wire at 75 degrees C with 6 gauge wire. So you have a 6 gauge wire, 80 amp breaker. People go crazy. Well, oh, no, this is how you do motors. Ryan?
Well, why don't you verbalize how you did that there?
Okay. Good point. I take the 28 amps. I said it, but I said it so fast. I take the feeder conductor on 430/24. I take the 28 amps times 125%, which is 35.
So the biggest motor? Is that
Well, I take the largest FLC.
okay?
Okay, take the largest FLC at 125%. That's 35. The 28 times 1.25, 35 plus 17, 35 plus 17. Oh, no, that's 45. That's 52, right? And so I need to have a 52 amp wire here and 75 degrees C, table 310, 15B16, and I guess that'd be 6 gauge wire on an 80 amp breaker. Thank you very much for slowing me down and having me repeat that.
Hey, Mike.
Yes.
I just really want to, I know you said this, but I really want to point out that when you do size the feeder protection, you're sizing it on the actual device, the largest actual device. So that's a 70 amp circuit protection on the largest device.
Yes, you saw that. Oh, I understand what you're leading
Yeah,
up
it
to.
has
I don't
to be
want to
the
go
lo-
there
right.
because somebody's, if they're tilting their head like a little puppy, wondering, I wonder what that means. And I'm not even going to go there. But there are some people that think something else. So you base it on the 70 amp breaker plus the FLC,
Right.
and I'll go there. There's a possibility that if I'd used a different current over here, that this could have come out to be, let's say, 68 amps. Well, if it's 68 amps for the branch circuit protection, you'd have put what? A 70 amp protection. But some people would have thought that you take the 68 amps plus the 17. Right. And I knew that's what you were leading up to,
Right.
Erica.
And
No. It's
very
not your
important.
calculation of the 250% plus the FLC at 100%. It's, well, you do your calculation, then you round up to your breaker, then you use your breaker plus your full load current. So I knew exactly where you were leading into. I was afraid to get in there because I was afraid we had it, but I felt that the guys could handle it, so let's just do that. Good point. 430-102 disconnect requirements, going to go very quickly. You need to have a disconnect for the motor, and you need to have a disconnect for the controller. And the disconnect for the motor must be within sight of the motor, and the disconnect for the controller must be within sight of the controller. Basic rule. You can, and this is your controller, a time clock. You can't have a controller ahead of the disconnect. Well, actually, this problem here is that you got to disconnect within sight of the controller. I'm sorry, within sight of the motor. Here's your controller, and the disconnect is not within sight of the controller. So in a swimming pool, you can't put a time clock before your disconnect because you got to be able to disconnect the controller. By the way, I didn't talk about the definition of a controller. And Ryan, look at that. I think the controller is probably defined in Article 100 because it would think, or is it on 430.2?
Well, you got to be careful because it's in both, but it's in two different contexts.
Oh, really?
There's an Article 100 controller and there's an Article 430 controller.
Well, okay. If the code in 430 uses the term controller and there's a definition of a controller in 430, then I'm not going to 100. You see how subtle this is in the code? You see how you got to really, really be aware? So what does 430.2 say as a controller? 430.
And the first part's important. For the purposes of this article, a controller is any switch or device that is normally used to start and stop a motor by making and breaking the motor circuit current.
Hold on. It's not the push button.
Right.
It's the making and breaking contacts.
Right.
That's the controller.
Yeah.
We're not going to get into that stuff, but I don't want people thinking
Right.
that you have a start-stop button, that is your controller. Okay, your controller is the actual, and we probably should, well, this is a manual controller, so it doesn't really matter here. Okay. All right, let's go on here. Here's your disconnect. It's within sight of the motor. That's your rule. Here's a disconnect within sight of the motor. The controller disconnect, which is within inside of the controller, can serve as a disconnect for the motor if the controller disconnect is within sight of the motor. So you have a disconnect for the motor within sight, a disconnect within sight of the controller, that's fine, or one disconnect can serve as a purpose of the disconnect of the controller as the motor, as long as it's within sight of the motor and the controller. 430.102b exception. You don't need to have a disconnect within sight of the motor if it's impractical. Well, what does it mean by impractical? I believe 430.102b exception has an informational note. And because this rule says, well, if it's impractical, I mean, you can't have a disconnect with the motor. It's not practical. You're like, how could it not be practical? Well, if the motor is in the bottom of a well, obviously your disconnect can't be within sight of the motor. Like, well, you got me on that one. I can see that now. Or if it induces a hazard to persons or property. So the other thing is, if it's not practical or it induces hazards to persons and property, there's an informational note. Ron, do you want to read me the informational note on 430.102b exception that describes, well, what could introduce an additional hazard to persons or property? That's 430. Again, you guys jump on that as I give you that reference. Ron, what does it say about it being the informational note there?
Yeah, it's right at the bottom of the page. They moved it. It says some examples of increased or additional hazards include, but aren't limited to, motors in excess of 100 horsepower, multi-motor equipment, submersible motors, motors associated with adjustable speed drives, and motors located in hazardous locations.
All right, hold 1 second. Read it again to me, and I'm going to parse you as we go along. Okay.
Some examples, motors in excess of 100 horse.
Okay. Eric and Victor, you guys deal with big stuff. And I don't know enough about motors, but apparently if you have a very large motor, you don't like go and just open the switch, right?
Yeah, and I tell you, there's a lot of motors nowadays that are being driven by VFDs, variable frequency drives, and you certainly do not want to have a field disconnect when there's a VFD-driven motor because you'll destroy your VFD.
Does it say that, Ryan, in the
Yeah,
information?
it talks about adjustable speed drives.
Yeah, so you have a variable frequency drive, you don't put a disconnect in the motor. I don't know enough about that, but apparently when you have the motor running, variable frequency drive, and then you open the switch, it does something to the equipment, and then all of a sudden you wipe out the electronics of the variable frequency drive. So the code recognizes these possibilities and say, well, yeah, okay, don't put a disconnect with inside a motor. Or in case you have hazard classified locations, maybe it's like, maybe you're better off not having a disconnect there in a classified location. So there'd be other possibility. But for 99% of the applications, a disconnect is going to be required within sight of the motor unless there's some compelling reason, as the code describes, and the information note provides as information and guidance. Let's go to 430. 430.103, operation of the disconnect. Pretty straightforward. The disconnecting means for a motor controller. Here's your controller right here. Ryan read it in 430.2. And the motor itself must open all ungrounded conductors simultaneously and be designed so that it won't close automatically. Well, if you're going to use your time clock, it's possible a time clock could possibly serve as a disconnecting means and could also serve as a controller. There's a possibility. But you might have time clocks that you can't turn it off, and all of a sudden you turn it off, and then you go into work on the motor, and then the time clock goes and turns it back on again. So just be careful. 430.107, readily accessibility. Either the controller disconnect or the motor disconnect required by 430.102 must be readily accessible. So here's an example of a controller disconnect that's readily accessible to the controller. Well, the disconnect from the motor is not readily accessible. And that's okay. One of the two of them have to be readily accessible. Hey, Victor, did you want to say something before we get off of Article 430?
Yes. VFDs, adjustable speed drives, are becoming more and more used in particularly industry and commercial use for energy management and energy reduction purposes. And that creates a problem with sizing the overcurrent protection here, and also we've talked about the problems with VFDs with the location of the disconnect. But in order to size the overload, we have to go to Article 430, 130A, and either 1 or 2, depending upon whether the manufacturer gives us instructions on this. 430, 130A1
gives, we size the, just like we normally would size any motor circuit. And if the manufacturer gives us instructions, we go to 430, 130A2, and then we have to follow his instructions on doing that sizing there. And it's generally going to be 125% rather than the 250, because we don't have that large impulse when the motor starts.
Now, what is the rule for sizing the conductors to the VFD?
Well, Mike, the conductor size is going to be given to us in 430, 122 A or B, and it's basically going to be 125% of the value of the VFD.
Excellent. All right, we are done with Article 430.